Chapter 3, Motionless Pulse Systems. The pulse devices mentioned so far have had moving parts, but rotating or fluctuating magnetic fields can be created without moving parts. An example of this is Graham-Gunderson's solid-state electric generator shown in U.S. Patent Application 2006/016397-1A1 of July 27, 2006, which is shown on page A, 1038 of the appendix. Another example is Charles Flynn's magnetic frame. Another device of this type comes from Charles Flynn. The technique of applying magnetic variations to the magnetic flux produced by a permanent magnet is covered in detail in the patents of Charles Flynn, which are included in the appendix. In his patent he shows techniques for producing linear motion, reciprocal motion, circular motion and power conversion, and he gives a considerable amount of description and explanation on each, his main patent containing 100 illustrations. Taking one application at random, he states that a substantial enhancement of magnetic flux can be obtained from the use of an arrangement like this. Here, a laminated soft iron frame has a powerful permanent magnet positioned in its center and 6 coils are wound in the positions shown. The magnetic flux from the permanent magnet flows around both sides of the frame. The full patent details of this system from Charles Flynn are in the appendix. Lawrence Tsiung's magnetic frame. Lawrence Tsiung has recently produced a subtle design using very similar principles. He takes a magnetic frame of similar style and inserts a permanent magnet in one of the arms of the frame. He then applies sharp DC pulses to a coils wound on one side of the frame and draws off energy from a coil wound on the other side of the frame. He shows 3 separate operating modes for the devices as follows. Lawrence comments on 3 possible arrangements. The first one shown above is the standard commercial transformer arrangement, where there is a frame made from insulated iron shims in order to cut down the eddy currents which otherwise would circulate around inside the frame at right angles to the useful magnetic pulsing which links the 2 coils on the opposite sides of the frame. As is very widely known, this type of arrangement never has an output power greater than the input power. However, that arrangement can be varied in several different ways. Lawrence has chosen to remove a section of the frame and replace it with a permanent magnet as shown in the diagram below. This alters the situation very considerably, as the permanent magnet causes a continuous circulation of magnetic flux around the frame before any alternating voltage is applied to the input coil. If the pulsing input power is applied in the wrong direction as shown here, where the input pulses generate magnetic flux which opposes the magnetic flux already flowing in the frame from the permanent magnet, then the output is actually lower than it would have been without the permanent magnet. However, if the input coil is pulsed so that the current flowing in the coil produces a magnetic field which reinforces the magnetic field of the permanent magnet, then it is possible for the output power to exceed the input power. The coefficient of performance or COP of the device is the amount of output power divided by the amount of input power which the user has to put in to make the device operate. In this instance the COP value can be greater than 1. As it upsets some purists, perhaps it should be mentioned that while a square wave input signal is applied to the input of each of the above illustrations, the output will not be a square wave, although it is shown that way for clarity. Instead, the input and output coils convert the square wave to a low-quality sine wave, which only becomes a pure sine wave when the pulse frequency exactly matches the resonant frequency of the output winding. The oscilloscope display shown here is a typical output power waveform which has nearly 390,000 of these pulses per second. There is a limit to this, as the amount of magnetic flux which any particular frame can carry is determined by the material from which it is made. Iron is the most common material for frames of this type, and it has a very definite saturation point. If the permanent magnet is so strong that it causes saturation of the frame material before the input pulsing is applied, then there can't be any effect at all from positive DC pulsing as shown. This is just common sense, but it makes it clear that the magnet chosen must not be too strong for the size of the frame, and why that should be. As an example of this, one of the people replicating Lawrence's design found that he did not get any power gain at all, and so he asked Lawrence for advice. Lawrence advised him to omit the magnet and see what happened. He did this and immediately got the standard output, showing that both his input arrangement and his output measuring system both worked perfectly well. It then dawned on him that the stack of 3 magnets which he was using in the frame were just too strong, so he reduced the stack to just 2 magnets and immediately got a performance of COP equal 1.5, 50% more power output than the input power. The transformers of Thane-Hines. Thane has developed, tested and applied for a patent for a transformer arrangement where the output power of his prototype can be 30 times greater than the input power. He achieves this by using a figure of 8 double toroid transformer core. His Canadian patent CA2594905 is titled Bitoroid Transformer and dated January 18, 2009. The abstract says, the invention provides a means of increasing transformer efficiency above 100%. The transformer consists of a single primary coil and 2 secondary coils. Magnetic flow is 1,000 times easier through iron than it is through air. Because of that fact, transformers are generally constructed on a frame made of iron or a similarly magnetic material. The operation of a transformer is nothing like as simple as school teaching would suggest. However, leaving parametric excitation aside for the moment, let us consider the effects of magnetic flow. The way that off-the-shelf transformers work at the moment is like this. When a pulse of input power is delivered to coil 1, called the primary winding, it creates a magnetic wave which passes around the frame or yoke of the transformer, passing through coil 2, called the secondary winding, and back to coil 1 again as shown by the blue arrows. This magnetic pulse generates an electrical output in coil 2, which flows through the electrical load, lighting, heating, battery charging, video displays, or whatever, providing it with the power which it needs to operate. This is all well and good, but the catch is that when the pulse in coil 2 finishes, it also generates a magnetic pulse, and unfortunately, that magnetic pulse runs in the opposite direction, opposing the operation of coil 1 and causing it to have to boost its input power in order to overcome this magnetic flow in the opposite direction, shown here by the red arrows. This is what makes current scientific experts say that the electrical efficiency of a transformer will always be less than 100%. This effect is caused by the magnetic path being symmetrical. Like the flow of electricity, magnetic flow passes along every possible path. If the magnetic path has low magnetic resistance, generally due to having a large cross-sectional area, then the magnetic flow through that path will be large. So, faced with several paths, magnetic flow will go along all of them in proportion to how good each path is for carrying magnetism. Thane-Hines has made use of this fact by making a transformer like this. This style of transformer has got quite complicated magnetic flows when it is operating, although the diagram above only shows some of the flow paths generated when the input coil 1 is pulsed. The really interesting result is seen when that input pulse cuts off and we expect return magnetic flow from coil 2 and coil 3. What happens is this. Assume that coil 2 and coil 3 are identical. The reverse magnetic flux coming out of coil 2 immediately encounters a junction with one path being far easier to use than the other. As a result, the vast majority of that magnetic flow follows the broad path, and only a small percentage flows through the narrow path. The broad path flow meets and is opposed by an identical large flow coming from coil 3, and those flows effectively cancel each other out. This produces a major improvement over an ordinary transformer. But, the small flow reaching the entrance to coil 1 encounters 2 identical paths, and only one of those paths goes to coil 1, so the flux divides with half going towards coil 3 and half going through coil 1. That halves the strength of the already small percentage of the original, unwanted reverse magnetic flow into coil 1. The other half runs into the reduced flow from coil 3 and those halves cancel each other out. The overall effect is a really major improvement in the performance of the transformer as a whole. In the patent document, Thane quotes a prototype test which had a primary coil winding with 2.5 ohms resistance, carrying 0.29 watts of power. The secondary coil 1 had a winding with 2.9 ohms resistance, receiving 0.18 watts of power. The resistive load 1 was 180 ohms, receiving 11.25 watts of power. The secondary coil 2 had a winding with 2.5 ohms resistance, and received 0.06 watts of power. Resistive load 2 was 1 ohm, receiving 0.02 watts of power. Overall, the input power was 0.29 watts and the output power 11.51 watts, which is a COP of 39.6, and while the document does not mention it directly, the primary coil should be driven at its resonant frequency. A variation of this arrangement is to attach an outer toroid to the existing bitoroid arrangement, like this. This prototype, as you can see, is fairly simple construction, and yet, given an input power of 106.9 milliwatts, it produces an output power of 403.3 milliwatts, which is 3.77 times greater. This is something which needs to be considered carefully. Conventional science say that there is no such thing as a free meal, and with any transformer, you will get less electrical power out of it than you put into it. Well, this simple-looking construction demonstrates that this is not the case, which shows that some of the dogmatic statements made by present-day scientists are completely wrong. At https://youtube/lbnnl4v8mq list equal plkh1zldxy1sy3 street 1 tutty 6 kiest kaig 9 Thane shows a video where his bitoroidal transformer is constructed from 3 ordinary toroids held together with cable ties. Thane then goes on to demonstrate the performance of this combination. The lead associated with the power being fed to the primary winding is so low that no light is visible. The output LED is lit so powerfully that the camera has difficulty in displaying it. The dummy load is a single resistor placed across the third winding, and there is a major performance difference when it is plugged into place. This video demonstrates very clearly the difference caused by using a bitoroidal transformer. This simple and elegant modification of the humble transformer converts it into a free energy device which boosts the power used to drive it and outputs much greater power. Congratulations are due to Thane for this technique and for his sharing it openly with anyone who is interested. The high-power motionless generator of Clement Figuera. In 2012, a contributor who uses the ID 1jabajak started a forum to investigate the work of Clement Figuera at http://www.overunity.com/12794/re-inventing-the-wheel part1-the-infinite-energy-ux-u9gzcqhqu. And member Hanlon 1492 contributed enormously by producing English translations of Figuera's patents. Clement Figuera of the Canary Islands died in 1908. He was a highly respected individual, an engineer and university professor. He was granted several patents and was known to Nikola Tesla. Figuera's design is very simple in outline. In 1902, the Daily Mail announced that Mr. Figuera, a forestry engineer in the Canary Islands, and for many years professor of physics at St. Augustine's College, Las Palmas, had invented a generator which required no fuel. Senor Figuera has constructed a rough apparatus by which, in spite of its small size and its defects, he obtains 550 volts, which he utilizes in his own house for lighting purposes and for driving a 20-horsepower motor. The Figuera device looks like a complicated transformer, but in fact, it isn't. Instead, it is 2 sets of 7 opposing electromagnets with an output coil positioned between each opposing pair of electromagnets. The physical position of the electromagnets and output coils is important as they are positioned very close to each other and there are induced magnetic fields between adjacent electromagnets and between the output coils due to their close proximity. The 2 sets of electromagnets are wound with very low resistance, high current wire or possibly, even with thick foil. The information given in the Figueira patent states that the electromagnets will be referred to in the patent by the letters N and S, and it is now thought that those two letters are deliberately misleading, as people tend to think of those letters referring to North Magnetic Pole and South Magnetic Pole, while in reality, the electromagnets almost certainly oppose each other, that is, with north poles facing each other, or possibly, with south poles facing each other. The arrangement is believed to be like this when seen from above. This arrangement creates a magnetic block wall, or magnetically null point, in the center of the yellow output coils, and the position of that magnetic balance point is very easily moved if the power supply to the two sets of electromagnets is altered slightly, and any movement of that magnetic balance point creates a substantial electrical output due to the alteration of the magnetic lines cutting the turns of wire in the yellow output coils. While the sketch shown above indicates a small gap between the electromagnets and the output coils, it is by no means certain that any such gap is needed, and while winding the three coils is more convenient if they are separate, when wound and being assembled, their cores may well be pushed together to form one continuous magnetic path. Another thing which has confused people, including me, is the drawing in the patent, which looks like an electrical commutator, but which is not part of the Figueira generator design. It looks like this. The dotted lines indicate internal electrical connections, so for example, contact 14 is connected to contact 3, but let me stress again that this unit is not part of the design, and while it is used to explain the actual operation, I would not be surprised if it were not intended to misdirect people from the actual operation. This point has been stressed, and it has been suggested that the actual working device is magnetic in nature and could be constructed like this. This looks like a very simple device, but it is an item of major importance in the Figueira design. First, the core is solid iron, sometimes called soft iron, but if you were beaten with a bar of it, you certainly wouldn't call it soft. The most important characteristic of such a core is its magnetic properties, as it is able to store energy. Please remember that this switching device is primarily magnetic in nature. It looks like this. This core is then wound with thick wire, perhaps AWG number 10 or 12 SWG, 2.3 x 2.3 mm square wire. The turns of wire should be tight, side by side, and sit exactly flat on the top surface as the wire there will be contacted by the sliding brush. The sliding brass contact or brush is dimensioned so that it connects across two adjacent wires, so that there is never any sparking as the brush contact slides around the circle of wires. The brush is driven by a small DC motor. In order for the sliding brush to contact the wire, the plastic insulation needs to be removed from the top half of the wire, with the remaining insulation keeping the turns from short-circuiting together. The wire is wound half of the way around the iron core, and a short length of wire is left to make an electrical connection. An additional winding is then made to cover the remaining half of the core, and again, a length for connection is left before cutting the wire. This gives you two windings, each covering 180 degrees around the core. The wire turns are strapped tightly with tape or cord wound around the side of the core, as that holds the wires securely in place. The two wire ends on each side are connected together, giving a 360-degree winding with good electrical connections 180 degrees apart. There are many ways to arrange the small DC motor so that it drives the brush slider. The motor could be mounted on a strip passing over the core, or on the baseboard, or to one side using a belt or gear wheel drive link. It does not matter which direction the brush moves around the core. The speed of rotation is not critical either, although it does determine the alternating frequency of the output. In most cases, the output will power a heating element or will be converted to DC to give the local mains frequency and voltage. When we first look at a device like this, we immediately think of the flow of electric current passing through the wire wound around the iron core. It appears as if the current is limited by the overall length of the wire between the brush position and the two outputs, but the reality is that while that is correct to a certain extent, the main control of the current flow is the magnetic field inside the circular iron core, and that field causes reluctance, resistance to current flow, proportional to the number of coil turns between the brush and each output. This alters the current flow to the set of N electromagnets compared to the current flow to the set of S electromagnets. As the magnetic intensity generated by the set of N electromagnets increases, the magnetic intensity generated by the set of S electromagnets decreases. But, as the magnetic power of the set of N electromagnets overcomes the magnetic field of the set of S electromagnets, that magnetic field gets pushed back into the soft iron core of the commutator device, essentially storing energy in that core. When the system needs to replace the energy lost in heating, it can use that stored magnetic energy in the commutator core, raising the overall efficiency. In this design, the current flowing through the electromagnets is always in the same direction and never drops to zero, merely oscillating in its intensity. The overall arrangement is like this. While the sketch above shows a 12-volt battery, there is no great reason why it should not be 24-volt or higher, especially if the wire used to wind the electromagnets is smaller diameter. The amount of power needed to create a magnetic field is not related to strength of the magnetic field, and a larger number of turns of thinner wire with a small current flowing through the wire can create a stronger magnetic field than few turns of thick wire with a large current flowing through those turns. The Alexker zero back EMF coils. Alex in Russia, who has shared several of his motionless pulse charging systems for batteries, now shares his design, which does not appear to have any back EMF effect on the primary coil. If that is the case, then any increase in output current draw does not have a corresponding increase in the current flowing through the primary coil. That is completely different to the way in which a conventional transformer operates. The arrangement is somewhat like the transmitter/receiver arrangement of Don Smith, and while it looks to be a simple arrangement, isn't. Alex draws his coil configuration like this. Here, his chosen form of construction is a frame of 12 lengths of 20 mm diameter plastic pipes, 4 at the top, 4 at the bottom and 4 verticals. Each pipe is filled with ferrite powder and there is an output coil wound on each of the 4 vertical pipes. Suspended in the center is the primary coil, which is 15 mm in diameter. All 5 coils are wound using 0.5 mm diameter enameled copper wire, SWG25 or AWG number 24. While Alex's drawing shows a single strand of wire, the actual arrangement for the 4 output coils is that they are wound as a single layer bifilar coil. For this, the output coils are wound with 2 strands of wire side by side, in a single layer along the length of the plastic pipe. Then, the start of one wire is connected to the end of the other wire. As the coils are filled with ferrite, they can operate at high frequency, when the 15 mm primary coil is fed with either DC pulses or an AC sine wave. Each output coil can provide a separate output, or the output coils can be connected in series to give a higher voltage or connected in parallel to give a higher output current. Alex also shows how ferrite toroids can be used, even with 220V mains, to give back EMF-free transformer operation. If the input frequency is as low as the mains, then the toroids may be iron dust types, or they can be constructed from iron shims in the same way that ordinary mains transformers are constructed. However, please understand clearly that the current flowing through any coil connected across a high voltage source such as 110V or 220V and using any of the following configurations, is limited by the impedance of the coil itself. Impedance is effectively AC resistance at the frequency of the AC voltage supply. If the coil impedance is low, then the current flowing through the coil will be high, and since the power dissipated by the current flow is voltage x current, the power dissipation with increased current goes up very quickly when the voltage level is as high as 220 volts. The power dissipation is in the form of heat, which means that with excessive power dissipation, the wire in the coil is liable to melt or burn out in an impressive flash of flame, smoke and blackened wire. Consequently, the coil winding needs to have many turns and the wire diameter needs to be sufficient to carry the current flow. The wire table on page 1 of the appendix shows the current which can be carried by each size of wire when wound into a coil. If there is no back EMF effect with the following configurations, then the current in the primary winding connected across the mains will not be affected by the other coils, so remember that when preparing the primary coil. The first arrangement uses 3 toroids to give 4 separate outputs. The amount of current which can be drawn from any secondary depends on the amount of magnetic flux which can be carried by the magnetic core or cores between the primary coil and that particular secondary coil. Obviously, the output current draw will also be limited by the current carrying capacity of the wire used in the secondary coil. If that level of current is exceeded for any length of time, then the insulation of the wire will fail, turns will short circuit together, the coil impedance will drop, the current increase further and the coil will burn out, so common sense is called for. Here, the primary coil 1 is wound on a toroid which is horizontal in the picture above, and the secondary coils 2 are wound on toroids which are shown as vertical in the drawing. The important point here is that the toroids with the secondary coils touch the primary coil toroid at right angles, that is, at 90 degrees. For convenience of winding the coils, any toroid can be assembled from 2 half toroids which allows the coil to be wound separately. And when completed, slid onto one of the C-shaped half toroids before the 2 halves are placed together to form the complete toroid. The second arrangement 3 toroids. The third arrangement uses 4 toroids, in a more powerful arrangement where the magnetic flux carrying capacity of the transformer is doubled as the cross-sectional area of the toroids inside each coil is doubled. This is a more difficult arrangement to construct, and if the coils are to be wound on a separate coil winder, then the toroids each need to be made from 1/2 toroid plus 2 quarter toroids so that the coils can be slipped onto 2 separate quarter toroid sections which are curving in opposite directions, unless of course, the inside diameter of the coils is a good deal larger than the toroid cross-section, which reduces the number of turns for any given length of coil wire. If these simple transformer arrangements operate as back EMF-free devices as claimed, then the current draw from any, or all, of the secondary windings does not have any effect on the current flowing through the primary coil. This is quite unlike present-day commercial transformers which are wound symmetrically, which in turn causes the current draw in the secondary coil to force an increased current in the primary winding. Alex also shows another arrangement which uses 7 toroids. He states that this arrangement is also free from the energy-wasting back EMF designs used at present in most commercial items of equipment. He specifies that the intended operating frequency is 50 Hz, which is the frequency of the mains, as the difference between 50 Hz and the 60 Hz used in America is not significant in any way. This frequency suggests that the toroids could readily be made of iron as in commercial transformers. The prototype was wound with 0.5 mm diameter wire and aimed at a power level of 100 watts. The capacitors are high-power oil-filled with capacitances up to 40 microfarad and rated at 450V when using 220V mains input. The tuning is very much like that of the rotoverter shown in Chapter 2. The physical layout is: the central toroid is wound all around its circumference as indicated by the blue color. This winding is fed directly with the input current source, which would normally be from the mains or from a mains transformer, probably at a lower voltage. There are then 12 output coils, 6 shown here in green and 6 shown in red. For best operation, each of these output coils need to be tuned to the central coil, and that needs to be done by altering the capacitor size by experiment to get the best performance from each coil. When properly set up, increasing the current draw from any of the output coils does not increase the power flowing into the central input coil. This contradicts what is normally taught in schools and universities, as they are only familiar with symmetrically wound transformers and motors where increased output current does indeed oppose the input power, causing increased input current and heat waste. The circuit is: the blue coil has the power input at A, and the capacitor in series with each coil is there to get all of the windings to resonate at the same frequency. The items B and C represent the useful load being powered by each coil. Although, obviously, only 2 of the 12 output coils are shown in the circuit diagram above, and there are an additional 5 green and 5 red coils which are not shown in the circuit diagram. It is probably worth remembering that adding a magnet to a toroid or closed-loop core transformer can boost the output provided that the permanent magnet is not strong enough to saturate the core completely and prevent oscillation of the magnetic flux. This has been shown by Lawrence Tsiung, Graham Gunderson and others, and so it might be worthwhile to experiment further with these configurations along the lines shown in the video at https://www.youtube.com/watch. The easiest version. Alex Kerr has produced a simplified Lenz law-free design, using commercial toroids already wound as step-down mains transformers. One supplier is http://www.electro-mpo.ru/card8524.html number sign VSV 7s with transformers of this type on offer. The technique is to remove the plate covering the central opening and connecting the 220V and 110V windings in series. Two of these transformers are used, each of them connected with their 220V and 110V windings wired in series, and then the toroids either placed side by side or alternatively stacked on top of one another with a 1 mm thick sheet of plastic between them. In the configuration where the toroids A and B are placed side by side, a power extraction winding D is wound between them. In the case where the toroids A and B are arranged in a stack with 1 mm plastic sheet between them, the power extraction winding D is wound around the two toroids, enclosing them both. While the winding D is shown as a narrow strip in the diagram, that is only to make the drawing easier to understand, as in reality, the winding D is continued all the way around the whole of the circumference of the toroids, and it can be many layers deep to suit the desired output voltage. Toroid A has a tuning capacitor C1 which is adjusted in value to achieve resonance in that circuit, as that minimizes the current flowing into toroid A from the mains. Toroid B has a capacitor C2 which is adjusted to give the highest output voltage, typically 600 volts, coming from toroid B. The purpose of toroid B is to divert the reverse magnetic flow in toroid A and so produce an efficient working system. The load L is in theory a dummy load, but in reality there is no reason why it should not be considered to be an actual working load if that output is convenient to use. The output winding D is free of the Lenz law effect, and the input current from the mains is not affected in any way when the current draw from coil D is increased, or even short-circuited. Alex Kerr stresses the fact that as the toroids are supplied already wound, this is actually a very easy design to replicate. The self-powered generators of Barbosa and Leal. In July 2013, two Brazilian men, Nilson Barbosa and Clariston Leal, published a series of patents which appear to be very significant. Their patent WO 2013/104042, published on July 18, 2013, is entitled Electromagnetic Device for Capturing Electrons from the Ground to Generate Electricity, and has some very interesting features. It describes a simple device which they describe as an electron trap. Their patents are written in Portuguese. An unusual feature of this design is the fact that it has a continuous conductive loop, in which it is claimed, current flows continuously, even without the need for an applied voltage. Instead, it is the magnetic fields of electromagnets which keep the current flowing. They state that an insignificant amount of input power produces a substantial power output, and they consider a COP of 100 to be about the minimum performance which can be expected from the design. That is a 1 watt input for a 100 watt output. One version of the electron trap looks like this. The inventors describe their device like this: this electromagnetic field generating device, powered by a power source, produces an electromagnetic field which induces an electric current in a closed conductive circuit, creating an interaction between the magnetic poles of the equipment and the magnetic poles of the Earth, through both electromagnetic attraction and repulsion. An endless supply of electrons is drawn from the Earth into the conductive closed loop, which is connected to the ground through a conductive interconnected grid. The attracted electrons add to the current already flowing in the conductive closed loop, making power available for driving high power loads, although the device itself is supplied with only a small amount of power. One very interesting feature is that the continuous loop coil formed by wire 4 in the diagram above, is literally, only 2 turns of wire. The power gaining mechanism, amazingly, is the earth wire, shown in blue, which is merely wrapped around wire 4 and not directly connected to it as the electron transfer link is by induction. With this arrangement, the current circulating in the closed loop wire 4, attracts more electrons from the ground, flowing through the wrapped connection of wire 5, into wire 4, augmenting the current flow there by a major amount. Wire 3 can have an alternating voltage applied to it in order to get alternating current in wire 4, but please understand that the current flowing in wire 4 is not the result of the current in wire 3. If the current in wire 3 is DC, then the current in wire 4 will be DC, as this is not a conventional transformer, but instead, it is an electron trap, operating in an entirely different way. The electron trap can be connected in an AC circuit of this type. Here, the earth wire 5 is wrapped around the continuous loop wire 4, feeding it additional electrons captured from the ground. The ends of wire 4 are connected together to form the loop, and that connection also forms the positive side of the output, where a DC output is being produced. The magnetic field produced by the current flowing in wire 3, acts on the electron flow coming from the earth, but as it does not provide any of the electric power flowing in wire loop 4, the current flowing in wire 3 can be tiny, without affecting the power output. In their patent WO 2013/104043, also of July 18, 2013, they show several different ways of connecting their electron trap in a useful circuit. For example, like this. Here, the battery 13, is used to power an ordinary inverter 12, which produces a high alternating voltage, in this case, at very low power. That voltage is applied to the wire 3.1 to 3.2 of the electron trap, creating an oscillating magnetic field, which creates an oscillating inflow of electrons into the closed loop wire 4, which creates an amplified electrical output at the same frequency, typically 50 Hz or 60 Hz, as those are the common mains frequencies. That amplified power output from the electron trap 14, is passed along wire 18 to an ordinary diode bridge 10, and the pulsing DC from the bridge is smoothed and used to replace the battery input to inverter 12. The battery is now switched out of the circuit and, as well as making the overall circuit self-powered, the power coming from the electron trap is used to recharge the battery if it needs recharging, or, perhaps, to charge the batteries of an electric car. Because the electron trap needs almost no input power at all, the input power to the inverter is very small, and so a good deal of additional AC power can be drawn off through cable 17, and used to drive powerful electrical loads, with no electrical power being needed from the battery. Being self-powered, the COP value for the circuit is infinity. Just as there are several different ways of using an electron trap in a circuit, there are several ways of constructing and connecting an electron trap. While it is possible to arrange the components so that the power output is 2-phase or 3-phase, here we will just deal with the ordinary, household, single-phase power supply. The first variation is to use more than one frame. 2 frames can be connected like this. This is the actual drawing from the patent, and it presents a slight problem in that it is not physically possible to implement the number 4 wire in the way shown. Each frame will have 2 complete turns wound on it, although the drawing does not show this. Because of the inaccuracy of the drawing, I am not able to say if the coil turns on frame 2, are in the same direction as those on frame 1. There are 4 possible ways of winding these 2 turn coils. When interconnecting them, so perhaps experimentation can be used to determine which method works best. With this 2-frame arrangement, there is just the one earth wire 5, as before, again, it is wrapped around wire 4. Rather than being physically connected to it. The continuous wire loop 4 has 2 ends as before, but there are now 2 3.1 wire ends and 2 3.2 wire ends. The Portuguese translation programs produce highly questionable results for this area of the patent, but I gather that the inventors intend the two 3.1 ends to be connected together and the two 3.2 ends to be connected together, and then the joined ends are treated exactly as before, effectively putting the two windings in parallel. One disadvantage of this design is that it is not portable due to the earth connection. Barbosa and Lille deal with this problem in their patent WO 2013/104041 of the same date, where they show a method of constructing an electron trap which collects excess electrons from the air. If you feel that there are no excess electrons in the air, then consider the fact that all of the aerial designs in Chapter 7 all extract and use those electrons. Also, consider the amount of electricity in a lightning strike, where much of the electrical energy comes from the air, and remember that worldwide, there are between 100 and 200 lightning strikes every second. The free electrons in the air electron trap is somewhat more complicated than the earth wire electron trap, with 4 pairs of coils, 3 and 4, being mounted inside 2 aluminium hemispheres. 1. The methods for using the air electrons trap are the same as those for the earth wire electron trap. An earth wire video demonstration is here. https://www.youtube.com/watchv=4 with 22 watts. Producing 6 kilowatts. To further research this invention, try the extensive information available via https://www.youtube.com/results search_query Barbosa plus E plus Lille. Barbosa and Lille advances. It is possible to operate the Barbosa and Lille style of circuitry without the need for an earth connection, by using the completed loop as a virtual ground. This is demonstrated by at his YouTube video channel at https://www.youtube.com/watchv=nk9yvl8xw, where he shows a 1400 watt vacuum cleaner being powered with just 15 watts of power being drawn from his mains wall socket. His unit is built into a red plastic box, which has a long input cable with a wall plug on the end, and the plastic box has a main socket installed on its lid. The input power shown on his watt meter is around 15 watts whether or not any output power is being drawn. He demonstrates the operation with a vacuum cleaner which draw around 1400 watts. The coefficient of performance is about 1400/15 = 93, which means that the output power is more than 90 times greater than the input power. The extra power is being drawn from the local environment. The circuitry inside his box is very straightforward, being just a continuous loop of very thick wire and a toroidal coil of much thinner wire. The thickness of the wire in the continuous loop is very important, as the current flowing in that loop is very high. The arrangement is subtle and you really need to understand what is going on. There has been a great deal of research and development on this device, and you can find a great deal of information on the web. For instance, http://barbosa-li-lurth-capture.blogspot.com/2017/02/building-my-first-full-scale-my-b.html. The first Barbosa and Lille replication. While many people have tried to replicate the Barbosa and Lille power generator design, which draws power from the earth, and failed, one man whose forum ID is Clarence read the relevant patents and knew immediately how the design works and what items in the patents are misdirection by Barbosa and Lille. He has built his own implementation of the circuit and it works perfectly. He has generously shared the relevant details. Please understand that what follows is not a description of where to start experimenting, but instead it is an actual working design. Build it as described and it will work. Build it differently and it won't work. Clarence has this to say. In the Barbosa and Lille patent they make a vague reference to the Lenz's law. It just so happens that this is the key to the whole device. On the Over Unity forum, a circuit diagram posted by member 00 showed the exact and complete method of defeating the Lenz's law, although most forum members did not seem to understand the importance of the circuit. However, I knew immediately that Lenz's law was just another name for back EMF. The Lenz's law effect is overcome by winding the single primary coil in a clockwise direction, and the AWG number 4 2.5 turn windings are wound on the bare core in an anti-clockwise direction, and that totally negates the Lenz's law. What does this achieve? It gets rid of the voltage component in the secondary windings, leaving only the amperage component. When you wind two toroids exactly the same using this method and connect them as shown below, you create a loop similar to a horseshoe magnet with a keeper on it, and the amperage in the loop just goes on circulating round and round as shown by Ed Leeds-Callan. This is the same principle. The loop has the ability within itself to add unlimited amperage instantaneously to the neutral green ground return wire accordingly as the load requires. The only limit to the available amperage is the current handling capacity of the looped black wire. You can touch the black wire loop connections with bare hands because as there is no voltage, there is no resulting shock. The connecting of the AWG number 10 phase wire to the bottom loop wire only serves to orient the polarization of the amperage. The oriented spinning of the amperage in the loop induces the amperage needed by the load into the captor output. This little toroid can allow the loop to load an AWG number 4 wire enough to melt it. The toroid primary wires live to live and neutral to neutral should be powered from the inverter by a separate circuit. Another separate circuit should be used with the live connected to the bottom black looped wire in order to polarize it. The neutral powers the input to ground. The return ground rods are linked in a series loop, and then, from a convenient ground rod to the green 2.5, turn loop around the black captor loop and then on to serve as the captor neutral to the load. You will know that you have enough ground rods when the captor RMS output voltage matches the RMS voltage of the inverter, and then, you will probably have to add about another 10 ground rods in order to keep the RMS voltage of the captor output from dropping. If the captor RMS output voltage drops, simple add more ground rods. Please understand clearly that without sufficient ground rods, the apparatus just will not work. Here is a connection pattern where many 6-foot, 1.8 m, long earthing rods are used. The direction of winding is vitally important, as are the wire sizes. You will notice that the windings on the two magnetic frames are in opposite directions, and the thick wire loop windings are both in opposite directions, and the thick wire winds also oppose the thin wire winding on the same frame. Looking from above, the thick wire forms the shape of the numeral 8. The thick wire is AWG number 4 with a diameter of 5.19 mm, and the other core windings are AWG number 10 with a diameter of 2.59 mm. The polarizing loop is produced by taking a few turns of the AWG number 10 wire around the insulation of the AWG number 4 wire. The wires inside the cables are not actually joined together. The input and output are marked as mains, as either 110V or 220V can be used, however, not actually fed from the mains, as that would create a ground loop, but instead, the input is from an inverter. The earth wire is AWG number 6 with a core diameter of 4.11 mm. While the magnetic frames above are shown as rectangular, they are actually circular toroids, which was what Barbosa and Lille used but failed to mention. The ones used by Clarence are type TD3001120 toroids with a diameter of 5.2 inches, 132 mm, and a thickness of 2.3 inches, 58 mm, each weighing 6.2 pounds, 2.8 kg, and available from http://www.tortran.com/standard_isolation_transformers.html. Clarence remarks that building this power generator replication is not cheap, and he has spent more than $2,000 on his replication. Mind you, with an output power of 3 kW, this unit meets all of his household electrical requirements. It is said that all builders should get a global or national geomagnetic map of their area before building, but Clarence says that he is in a dead area anyway, so there is probably little point in this, as the number of earthing rods needed in your area is found by trial anyway, and knowing in advance does not change that number. Here are some pictures of Clarence's successful build. Components used were toroids, Bridgeport Magnetics. Tortran, in stock standard design toroid isolation transformers, Bridgeport Magnetics Group. Contact, Michael Carraz. Email, sales@bridgeportmagnetics.com. Tortran Division, contact us, Bridgeport Magnetics Group. Custom ordered toroid, 2 required. TD 300, 1120, P, 300 VA, 60 Hz, primary 120 V, 160 degrees winding on toroid surface, no secondary winding. $125 USD each. Smart Battery Charger. Xantarix True Charge 2 Battery Charger, 20 AMP model. Website, True Charge Battery Charger True Charge 220A, 40A, 60A Xantarix. Xantarix Dealers List. Where to buy, in America. Available from Amazon.com. Amazon.com, Xantarix 804, 1220, 02 True Charge 212V20A Parallel Stackable Battery Charger, GPS and navigation. Looks like the price is around $260 to $300 USD, depending where you order from. Minimum recommended battery bank size for use with the 20 AMP charger model is 40 Ah. 12V pure sine wave power inverter. Ames Power 3000 Watt 12V DC pure sine wave power inverter, model, PWRIG 300012120S. Website, http://www.amescorp.net/3000-watt-pu. Inverter.html. Available from Invertersrus, $699 USD. http://www.invertersrus.com/ames-pwrig 300012120s.html. Amazon, $799 USD. http://www.amazon.com/ames-power-pwr. Plus Wave Plus Inverter. Forum moderator level who has done an excellent job of retrieving and displaying Clarence's material here. http://www.energeticforum.com/renewable-energy/2009-barbosa-lil-devices-2.html, says. Stick to the battery and inverter method as the power source, as that is the only way you can avoid a ground loop to the mains electrical power system. The one exception is you might be able to avoid such a problem when powering from the mains if you use an isolation transformer, but isolation transformers can be expensive and have a limited capacity as well. Caution, also beware that an inverter with an output of 120 volts or 240 volts can kill you if you touch live wires, so don't build such a setup if you don't understand such things. You need to take necessary safety precautions. Free energy from Lori Matchett. The style of operation used by Barbosa and Lil looks as if it is related to the developments of Lori Matchett. On June 16, 2008, Lori Matchett published his very simple design for a device which captures usable free energy, video, http://utuesday.be/egd907d428 right parenthesis. His device is based on a very simple and well-known principle of static electricity. This is a principle which is taught in schools all around the world but is generally considered to be of no importance as static electricity is considered too low power to be of any use. I seriously doubt that anyone who has been struck by lightning would consider static electricity to be low power, and suggesting that to them is likely to expand your vocabulary with some words which are seldom heard. Important note, the following details mention the use of mains voltages, and so let me stress that this presentation is for information purposes only and must not be construed as being a recommendation that you construct or use any such device. Should you choose to ignore this and construct and use Lori Matchett's device, then please be fully aware that you do so entirely at your own risk and nobody else is in any way responsible for the results of what you do. The principle which is being used here is that an electrically charged object causes the migration of opposite charges on the surface of any object brought close to it. For example, if a charged surface if brought close to a metal sphere, then this happens. The ordinary metal sphere B, which has no particular charge on it, is very much affected by being close to a charged surface A, and the closer it gets, the greater the effect. The surface of the sphere had an even distribution of positive and negative charges on its surface, giving it an overall charge of about 0, but the charged surface changes all that. The positive charges on surface A attract the negative charges on the surface of the sphere, causing them to migrate towards surface A. While the positive charges on surface A do repel the existing positive charges on the surface of the sphere, the migrated negative charges of the sphere itself have an even greater effect, causing the segregation of electrical charges shown above. The situation returns to normal if the sphere is moved away again. However, the situation changes considerably if the metal sphere B is connected to the ground. The movement of charges on the surface of the sphere is the same as before, but the Earth has millions of spare charges of both kinds, and so, immediately siphons off the excess positive charges on the side of the sphere away from charged surface A. You will notice that charged surface A is not directly involved in any way, and no charge moves from A to B. The same effect is seen if the surface A is negatively charged, except for the fact that the sphere has positive charges rather than the negative charges shown above. The only current flow is along the wire connecting the sphere to the Earth connection. Laurie Matchett uses this principle, and for the charged surface he connects one end of a brass rod to the live side of a 100V 60 Hz mains electricity supply. The other end of the brass rod is not connected to anything else. This produces the situation for 8.3 milliseconds. And then for the following 8.3 milliseconds the mains reverses and you get this situation. The result of this is that there is a backwards and forwards flow of static electricity along the Earth connecting wire, a flow which reverses direction 60 times per second. This is not conventional electricity but is the same form of electricity which is collected by an aerial. Nikola Tesla's patents show many different ways of utilizing this static electricity, as does Herman Plausen in his patent, www.free-energy-info.com/chapter7.pdf right parenthesis. Thomas Henry Moray produced 50 kilowatts of continuous power from quite a small aerial. Paul Baumann of the Swiss Commune produced several kilowatts from static electricity. Laurie Matchett settles for just a few watts, and he does it like this. He connects the live wire of a 110V, RMS, AC mains supply to a brass rod 28 inches, 710 mm, long and 3/16 inches, 4.76 mm, in diameter. The rod is not directly connected to anything else and so does not form part of a closed-loop circuit, and so, no current flows from the mains. It must be stressed that the rod and connecting wire are potentially very dangerous and need to be insulated very carefully to ensure that touching them will not cause an electric shock. Please understand very clearly that as no current of any kind is drawn from the mains, that the circuit is not stealing electricity from the mains. For convenience, and only for convenience, Laurie uses the earthing system of the house mains supply by connecting a green earthing wire to the earth pin of his mains plug. It needs to be clearly understood that this has nothing directly to do with the mains supply, and any good quality separate earth would be at least as good as the earthing point inside the mains plug. Effectively, there is only one mains connection. Instead of using a metal sphere as shown in the illustrations above, Laurie uses a coil of wire wound around the insulation layer on his brass rod, and he passes the alternating flow of static electricity, drawn from the earth, through a standard diode bridge as shown here. Laurie covers the brass rod with insulation which is as thin as possible. He suggests heat shrink tubing for the insulation, and on top of it he winds 0.405 mm diameter, solid core enameled copper wire, covering a 24-inch, 610 mm, length of the rod, placing the turns closely side by side and leaving 2 inches, 50 mm, clear at each end of the rod. Thicker wire should not be used. He also shows a 500 mA fuse in the main supply line. I am not at all happy about that, as that fuse can power 5 incandescent 100-watt mains bulbs connected in parallel, and do you really want that amount of power flowing through you if your insulation is not good enough and you touch it? If you use a fuse in that position, I would suggest a 20 mm glass quick blow 100 mA fuse, mainly because no smaller one is readily available. The fuse is not needed for the circuit and is there in an attempt to protect careless humans. The coil wound on the insulated brass rod is only connected at one end, and that end goes to one of the two alternating current tags on a 3A diode bridge. Lori does not specify the voltage rating for the diode bridge, but it needs to be a minimum of 170 volts if the mains is a 110V RMS type, and double that for a 220V RMS mains connection. I have no idea why he specifies a 3 amp rating, but the minimum bridge available locally at 3 amps, which I would recommend, is a 400V rated unit which is supplied at trivial cost. We need to understand the effect of the diode bridge. It halves the available voltage and doubles the frequency as illustrated here. A 110V supply is supposed to swing from -155V to +155V and back again 60 times per second, which is an overall voltage swing of 310V. When passed through a diode bridge, that changes to a voltage waveform, which swings from 0 volts to +154V and back again 120 times per second, which is an overall voltage swing of 154V, which is an average or RMS voltage of 109V due to the sine wave shape. In the rest of the world, the mains voltage is 220V, RMS, nominal, alternating 50 times per second, and the live mains wire is color-coded brown in the UK and the earth wire yellow/green stripes. In passing, the neutral wire is white for the American 110V system and blue for the 220V system used in the UK. This design has been brought to my attention by Jess Ascanius of Denmark, who is a very able developer of all kinds of free energy designs. He has replicated this design of Lori Matchett and confirms that it works. He has also taken the design further and shares some of the practical details which he has discovered through his own experimentation. For greater power, additional rods can be used. While brass is considered to be the best material for the rod, the diameter is not critical in any way, and any size from 5 mm to 20 mm can be used, and instead of a rod, a length of brass pipe should be quite suitable. It is also possible to use other materials for the rod, but doing that reduces the output power available. Jess has checked the output of his implementation with the mains fuse removed. The result was an output voltage of 26V picked up from the many 220V 50 Hz signals generated by the mains wiring all around the place for lighting and sockets. When the fuse is inserted, the voltage rises immediately to 129V with 2 rods or 162V with 5 rods. When that voltage is loaded with a 7-watt LED lighting array, the voltage gets pulled down to 61V, but good lighting is being produced for zero current draw from the mains. I would expect that putting a reasonably large capacitor across the load, that the reservoir effect of the capacitor would improve the LED output. Jess initially used 2 long rods wound with coils, and later, 5 rods. His AC ammeter is sensitive enough to show that due to inefficiencies caused by the tiny stray capacitance between the rods and the coils, there is a very slight current draw from the mains. The mains wattage is far less than the output wattage of the system. An improvement implemented by Jess is adding 4 high-speed BYV27 diodes to the ordinary diode bridge like this. This has the effect of improving the action of the diode bridge and allows more power to extracted from each cycle of the energy flow. When using 2 brass rods, Jess gets his 5-watt LED array to light up like this. Lori also extended his development to a remarkable 48 rods. Video link, http://utuesday.be/hjyzk69qc. The electrical output could be used to charge batteries. Adding extra turns does not increase the output voltage. If the number of turns in each coil matches the output load, then the output power will be greater. Alexker in Russia, who is expert in recharging batteries, has experimented with this concept, and he uses 10 coils connected in parallel. He does not use brass, but instead uses the much shorter 300 mm long, 3 mm diameter welding rods with their chemical coating removed. Also, these rods are only used to raise the effectiveness of 2 separate coils wound on each rod. Each coil is 700 to 750 turns of 0.4 mm diameter wire, and the connections are made to the coils and not the rods, as shown here for a single coil pair. Alex isolates his set of 10 coil pairs inside a short length of plastic piping, and uses them to power his battery charging circuit. Some people claim that these machete-style circuits just draw power from the mains. I do not believe that that is the case, although there is a very small leakage caused by the slight capacitance between the coils and the rods, and that is indeed charged for by the electricity supply company. For drawing power from the mains, a circuit like this is used. Here, the output voltage is determined by the number of turns in the coils, and the available current is controlled by the number of rods involved. You will notice that these circuits have connections only to the mains and nowhere else. These are not circuits which I use, nor do I recommend that you use it either. The green bars are iron welding rods with the chemical coating removed. These are then wound with a single layer of 0.5 mm diameter enameled copper wire, that is SWG25 or AWG24 size wire. A power hand screwdriver is said to be good for coil winding like that. The side-by-side wire coil is then coated with shellac or high-voltage varnish. I am told that with 220V mains power and a 1A diode bridge, that power can be drawn from the circuit without anything being recorded on the electricity supply meter. This is a seriously dangerous circuit, as it can produce high voltage at the output of the bridge, and that power could kill you. No power drain is recorded, presumably because the coils are wound in opposing directions. Now that is a circuit which could be considered to steal power from the mains. The matchet-style circuit is different in that the power flows through the circuit from the ground. Barbosa and Lille demonstrated 169 kilowatts of power flowing from the ground, and as they powered their circuit from a battery-driven inverter and not the mains, there was definitely no question of stealing mains power. The battery input also allowed them to establish the actual performance as 104 times more energy flowing out of their circuit than the energy flowing into it. Actually, I'm not at all convinced that the circuit shown above does actually draw net power from the mains. The mains meter charges you for power assessed by multiplying the average voltage by the average current, even when those two are out of step and you receive less power than you are charged for. In this instance, if no current draw is registered on the meter, then perhaps as a result of the opposing direction coils, the power drawn is matched by an equal amount being returned to the mains, and there may not be any real net current draw. Either way, I do not recommend the use of these circuits. The solid-state magnetostrictive system of Annis and Eberle. Theodore Annis and Patrick Eberle have produced a variation on this multiple magnetic path method, which is shown in their U.S. patent application 20090096219. They have opted to use a motionless reluctance switch, which is a solid-state device which can block magnetic flow when energized. They have arranged one of their devices like this. The ring shown in gray is a magnet which connects to the ring shown in yellow through two diagonal reluctance, magnetic flow, switches. The yellow ring can carry magnetic flux, and the control box marked 118 switches the diagonal strips on and off in turn, causing the magnetic flux to reverse its direction through the yellow ring. The coils wound on the yellow ring pick up this reversing magnetic flux and pass it out as an electric current. While only one pair of rings are shown here, the design allows for as many rings as are needed to be connected together as shown here. The patent says, the currently preferred motionless reluctance switch is described by Toshiyuki Ueno and Toshiro Higuchi, in their paper entitled Investigation of the Dynamic Properties of a Magnetic Flux Control Device. Composed of laminations of magnetostrictive piezoelectric materials, University of Tokyo 2004. As shown in Fig. 4, This switch is made of a laminate of a giant magnetostrictive material 42, a terabyte Dy-Fe alloy, bonded on both sides to a piezoelectric material 44, 46 to which electricity is applied. The application of electricity causes the reluctance of the piezoelectric material to increase. This original patent application is included in the appendix. However, very interestingly, there is another, completely different patent application from Annis and Eberle, with the same publication date and the same number. It is not at all obvious to me how that could be, but here is the bulk of that other patent application, the original being in the appendix. Energy generation apparatus and methods based upon magnetic flux switching. Abstract. In an electrical energy generator, at least one permanent magnet generates flux and a magnetizable member forms the single flux path. An electrically conductive coil is wound around the magnetizable member, and a plurality of flux switches are operative to sequentially reverse the flux from the magnet through the member, thereby inducing electrical current in the coil. A figure of 8 construction comprises 2 continuous loops of magnetizable material sharing a magnetizable member common to both loops. An alternative configuration uses stacked loops and a separate piece of material acting as the magnetizable member. One end of the magnet is coupled to one of the loops, with the other end being coupled to the other loop. Each loop further includes 2 flux switches operated in a 2x2 sequence to sequentially reverse the flux through the magnetizable member. A relatively small amount of electrical power is used to control the magnetic flux of a permanent magnet by switching the flux between alternate paths. The resulting power from the switched magnetic flux yields substantially more power than the power required for the input switching. Description. Field of the invention. This invention relates generally to energy generation and, in particular, to methods and apparatus wherein magnetic flux is switched through a flux path to produce electricity. Background of the invention. Magnetic flux may exist in free space, in materials that have the magnetic characteristics of free space, and in materials with magnetically conductive characteristics. The degree of magnetic conduction in magnetically conductive materials is typically indicated with a BH hysteresis curve, by a magnetization curve, or both. Permanent magnets may now be composed of materials which have a high coercively, Hc, a high magnetic flux density, Br, a high magnetomotive force, mmf, a high maximum energy product, Bhmax, with no significant deterioration of magnetic strength over time. An example is the Endfeb permanent magnet from Vac of Germany, which has an Hc of 1,079,000 amperes/meter, a Br of 1.427 Tesla, an mmf ranging up to 575,000 ampere turns, and a Bh max of 392,000 joules/meter 3. According to Moskowitz, Permanent Magnet Design and Application Handbook 1995, page 52, magnetic flux may be thought of as flux lines which always leave and enter the surfaces of ferromagnetic materials at right angles, which never can make true right-angle turns, which travel only in straight or curved paths, which follow the shortest distance, and which follow the path of lowest reluctance, resistance to magnetomotive force. Free space presents a high reluctance path to magnetic flux. There are many materials which have magnetic characteristics similar to those of free space. There are other materials which offer a low or lower reluctance path for magnetic flux, and it is these materials that typically comprise a defined and controllable magnetic path. High-performance magnetic materials for use as magnetic paths within a magnetic circuit are now available and are well suited for the rapid switching of magnetic flux with a minimum of eddy currents. Certain of these materials are highly nonlinear and respond to a small applied magnetomotive force, mmf, with a robust generation of magnetic flux, B, within the material. The magnetization curves of such materials show a high relative permeability, or, until the knee of the curve is reached, at which point or decreases rapidly approaching Unity as magnetic saturation, BS, is reached. Some of these nonlinear, high-performance magnetic materials are referred to as square due to the shape of their BH hysteresis curves. An example is the FINEMET registered feat, 3H nanocrystalline core material made by Hitachi of Japan. Other examples include Superperm 49, Superperm 80, Supermalloy, Supersquare 80, Square 50, and Supermender, which are available from Magnetic Metals in the USA. A reluctance switch is a device or means that can significantly increase or decrease, typically increase, the reluctance of a magnetic path. This is ideally done in a direct and rapid manner, while allowing a subsequent restoration to the previous, typically lower, reluctance, also in a direct and rapid manner. A reluctance switch typically has analog characteristics. By way of contrast, an off/on electric switch typically has a digital characteristic, as there is no electricity bleed-through. With the current state of the art, however, reluctance switches exhibit some magnetic flux bleed-through. Reluctance switches may be implemented mechanically, such as to cause keeper movement to create an air gap, or electrically by various other means. One electrical reluctance switch implementation uses a control coil or coils wound around a magnetic path or a submember that affects the path. U.S. Navy publication, Navy Electricity and Electronics Series, Module 8, Introduction to Amplifiers, September 1998, page 3-64 to 3-66 describes how to modulate alternating current by changing the reluctance of the entire primary magnetic path by these means, one of which is used in a saturable core reactor and the other in a magnetic amplifier. Flynn, U.S. Pat. Number 6246561, Patrick E.T. Alabama, U.S. Pat. Number 6362718, Pedersen, U.S. Pat. Number 6946938, Marshall, and U.S. Patent Application 2005/01256702, A1. All disclose methods and apparatus that employ this type of reluctance switch for switching magnetic flux from a stationary permanent magnet or magnets for the purpose of generating electricity, and/or motive force. Another electrical means of implementing a reluctance switch is the placement within the primary magnetic path of certain classes of materials that change, typically increase, their reluctance upon the application of electricity. Another electrical means of implementing a reluctance switch is to saturate a subregion of a primary magnetic path by inserting conducting electrical wires into the material comprising the primary magnetic path. Such a technique is described by Conrad and Brudney in an improved method for virtual air gap length computation, in IEEE Transactions on Magnetics, Volume 41, Number 10, October 2005. Another electrical means of implementing a reluctance switch is described by Valery Ivanov of Bulgaria on the website www.inkomp-delta.com, shown in Fig 1. An electric toroid 110 is inserted into a primary magnetic path, 100. So that the primary magnetic path is divided into two subpaths 110A and 110B. A net magnetic flux reduction effect in the primary magnetic path 100 results from the combination of the effects in the two subpaths 110A and 110B, each of which results from different physics principles. In the first subpath 110A, the magnetic flux generated by applying electrical current to the windings 110 around toroidal path 110 opposes and subtracts from its portion of the magnetic flux 103 received from the primary magnetic path 100, yielding a reduced magnetic flux, which is also further reduced by a decrease in the subpath 110A's relative permeability, thereby increasing the reluctance of the subpath. In the second subpath 110B, the magnetic flux generated by applying electrical current to the toroid windings 111 adds to its portion of the magnetic flux 103 received from primary magnetic path. 100 yielding an increased net magnetic flux that approaches or exceeds the knee of the material's magnetization curve, thereby reducing its relative permeability and increasing its reluctance. Summary of the invention. This invention is directed to methods and apparatus where magnetic flux is switched in both direction and intensity through a flux path to produce electricity. The apparatus broadly comprises at least one permanent magnet generating flux, a magnetizable member forming the flux path, an electrical conductor wound around the magnetizable member, and a plurality of flux switches operating to reverse sequentially the flux from the magnet flowing through the member, thereby inducing electrical current in the coil. The preferred embodiment includes first and second loops of magnetizable material. The first loop has 4 segments in order A, 1, B, 2, and the second loop has 4 segments in order C, 3, D, 4. The magnetizable member couples segments 2 and 4, and the permanent magnet couples segments 1 and 3, such that the flux from the magnet flows through segments A, B, C, D and the magnetizable member. 4 magnetic flux switches are provided, each controlling the flux through a respective one of the segments A, B, C, D. A controller is operative to activate switches A, D and B, C in an alternating sequence, thereby reversing the flux through the segment and inducing electricity in the electrical conductor. The flux flowing through each segment A, B, C, D is substantially half of that flowing through the magnetizable member prior to switch activation. The loops and magnetizable member are preferably composed of a nanocrystalline material exhibiting a substantially square BH intrinsic curve. Each magnetic flux switch adds flux to the segment it controls, thereby magnetically saturating that segment when activated. To implement the switches, each segment may have an aperture formed through it and a coil of wire wound around a portion of that segment and through the aperture. The controller may be at least initially operative to drive the switch coils with electrical current spikes. The first and second loops may be toroidal in shape, and the loops may be spaced apart from one another, with A opposing C, and 1 opposing 3, and with B opposing D and 2 opposing 4. The magnetizable member in this case is preferably a separate piece of material. Alternatively, the first and second loops may form a figure of 8 shape, with the 2 loops intersecting to form the magnetizable member. The permanent magnet, S, and the material comprising the magnetic paths are preferably proportioned such that the material through the common segment is at or slightly below its maximum relative permeability before the electrically conducting output coil is energized. In the preferred embodiments, the power resulting from the switched magnetic flux yields substantially more power than the power required for the input switching. Brief description of the drawings. Fig 1 is a drawing of a prior art reluctance switch in the form of an electrical toroid inserted into a primary magnetic path. Fig 2 is a detail drawing of a reluctance switch according to the invention. Fig 3a and Fig 3b are detail drawings showing the use of 4 reluctance switches according to the invention. Fig 4 is a drawing which depicts a preferred embodiment of the invention. Fig 5 is a detail drawing an alternative reluctance switch according to the invention implemented through split laminations. Fig 6a and Fig 6b show the operation of an energy generator according to the invention. Fig 7a is an exploded view of a preferred energy generator construction. Fig 7b is a side view of the construction shown in Fig 7a. Fig 8 is a simplified schematic diagram of components used to simulate the apparatus of the invention. Fig 9a is a diagram that shows the current delivered to one pair of flux switches in the simulation. Fig 9b is a diagram that shows the current delivered to the other set of flux switches in the simulation. Fig 10 shows the output of the simulation shown here, and Fig 11 is a block diagram of a controller applicable to the invention. Detailed description of the invention. Fig 2 is a detail drawing of a reluctance switch according to the invention. The reluctance switch includes the following components: a closed magnetic path 110 comprised of a high-performance magnetic material, preferably a nonlinear material exhibiting a sharp knee as saturation is approached, around which is wound a coil 111. The closed magnetic path 110 shares a common segment 101 with a primary magnetic path 100, in which magnetic flux 103 is induced by a permanent magnet, shown in subsequent drawings. Electric current is applied to windings 111 having a polarity and sufficient amperage so that the magnetic flux generated in the path of switch 110 is additive to the magnetic flux 103 from the permanent magnet, such that the primary path 110 approaches or reaches magnetic saturation. Fig 3a and Fig 3b are detail drawings of an apparatus which employs 4 reluctance switches according to the invention in a manner similar to that disclosed in U.S. Patent Application Serial No. 11/735, 746 entitled Electricity Generating Apparatus utilizing a single magnetic flux path, the entire content of which is incorporated herein by reference. In this and in all embodiments described herein, the geometry of the closed magnetic paths may be circular, toroidal, rectangular, or any other closed path shapes. A primary path 304 carries the flux from permanent magnet 302 unidirectionally. Flux switch pairs 310A/E and 310B/D are activated in alternating fashion to reverse the flux in magnetizable member 304C, thereby inducing electrical current in winding 330. Fig 3a shows the flux flow in one direction, and Fig 3b shows it reversed. In Fig 3a, switches 310A and 310E are activated by controller 320 in electrical communication with the windings on the switches such as through conductor 322 to winding 324. The additional flux in switches 310A and 310E are additive with the flux that would otherwise be present in segments 304A and 304E, thereby saturating these paths, causing the flux through segment 304C to be in the direction shown. In Fig 3b, switches 310B and 310D are activated, saturating segments 304B and 304D, and reversing the flow. Fig 4 is a drawing that depicts an embodiment of the invention using circular toroids 400, 401 and multiple permanent magnets 402, 403 disposed in the primary path 404. The two toroids 400, 401 intersect, forming magnetizable member 404E. A coil 430 is wound around the member 404E, as shown. The primary magnetic path 404 interconnects the upper end of loop 400 and the lower end of loop 401. One of the magnets, 402, couples one end of the primary magnetic path 404 to the first loop 400, and another, 403, couples the other end of the primary magnetic path 404 to the second loop 401. In this, and all of the embodiments described here, the permanent magnets are strong, rare earth magnets, and multiple magnets of any length, thickness, may be used in each case. Further, in all embodiments, the loops, primary magnetic path and / or magnetizable member are preferably constructed from a high magnetic permeability material such as the FINEMET feet, 3H nanocrystalline soft magnetic material available from Hitachi. The invention is not limited in this regard, however, as alternative materials, including laminated materials, may be used. The connections of the primary magnetic path 404 to the two-loop 400, 401 create 4 segments apart from the magnetizable member 404E, the 4 segments including 2 opposing segments A, B in the first loop on either side of magnet 402, and the 2 opposing segments C, D in the second loop on either side of magnet 403. 4 magnetic flux switches are provided, each being operative to control the flux through a respective one of the 4 segments. A controller 420 is operative to activate the switches associated with segments A and D, and then B and C, alternately, thereby reversing the flux through the member 404E, and so, inducing electrical current in coil 430. Apertures may be formed through each of the 4 segments, with the switches being implemented by coils 410A to 410D which pass through the apertures and around an outer, or inner, portion of each segment. As shown in Fig 5, if the loops are fabricated with laminated material 502, the laminations may be split at 506 to accommodate coil 504. The percentage of the segment surrounded by the coil may vary in accordance with the material used. The waveforms presented to the coils, and other factors, with the goal being to magnetically saturate each segment through activation of the associated switch, thereby reversing the flux through path 404E. Fig 6a and Fig 6b show the operation of the apparatus of Fig 4. The primary path 404 carries the flux from permanent magnets 402 and 403 unidirectionally. Reluctance switches 410A to 410D are activated alternately to reverse the flux in segment 404E which, in turn, induces electrical current in winding 430. Fig 6a shows the flux flow in one direction, and Fig 6b shows it flowing in the opposite direction. In Fig 6a, switches 410A and 410D are activated by controller 420 in electrical communication with the windings on the switches, such as through conductors 422 to switch 410B. The flux provided by switches 410A and 410D, thereby saturating these paths, causing the flux through segment 404C to be in the direction shown. In Fig 6b, switches 410B and 410C are activated, saturating segments 404B and 404D, thereby reversing the flux through path 404E. Fig 7a depicts a preferred construction of the apparatus depicted in Fig 4, Fig 6a and Fig 6b. Loops 400 and 401 are implemented as complete toroids 700, 701. This is important, since preferred high-performance magnetic materials are currently available in regular shapes of this kind. Note that, in this case, curved slots such as 770 are formed through the sides of each toroid to implement flux switches A to D. The magnetizable member in this embodiment is implemented with a block of material 704, preferably the same high-performance magnetic material used to construct loops 400, 401. Permanent magnet 702, shown at 702, preferably has the same length as block 704, enabling the various constituent parts to be held together with compression, shown in Fig 7b. The following sections summarize some of the important characteristics of the preferred embodiments. In terms of materials, the apparatus benefits from the use of nanocrystalline material with a square BH intrinsic curve, a high BR remanence, which is about 80% of its BS saturation, a low HC coercivity, and a fast magnetic response time to saturation. An example is fine met feet 3H from Hitachi of Japan, which has a BR of 1.0 Tesla, a BS saturation of 1.21 Tesla, a time to saturation BS of 2 USEC, and an HC of 0.6 amp turn/meter. Modern permanent magnets are used with a square BH intrinsic curve, a BR in the range of 1.0 Tesla or more, and high HC in the range of 800, 000 amp turn/meter or more. An example is the Endfeb magnet from the German company VAC, which has a BR of 1.427 Tesla and an HC of 1.079, 000 amp turn/meter. An important consideration is the matching of the magnet to the nanocrystalline material, both in Tesla rating and in cross-sectional area. The magnet's BR should be below the BS of the nanocrystalline material. If the magnet is too strong for the nanocrystalline material, this may cause the nanocrystalline material to saturate at the area of contact with the magnet. The current driving the reluctance switches in the prescribed 2x2 sequence should have a sharp rise in the leading edge, TR, of each pulse with a pulse width, PW, and amperage value that are sustained until released at the end of the pulse width, TF. The table below shows the effects of input current pulse rise times, TR, on the output. There exists a narrow band of TR, before which there is small power output, at which there are excellent power output and COPs in the range of 200 to 400 or greater, and after which there is no major increase in power output. The COP of this device without the coupling circuit is defined as output power/drive power for the switches. Valery Ivanov's motionless generator. There are other devices which have what appears to be a very important air gap in a magnetic frame. One of these was displayed on a Bulgarian website and is on the web page, which is located at http://www.incompdelta.com/page3.html, put up by Valery Ivanov in 2007. Valery lives in Elendpolin, Bulgaria, and his motionless generator has COP equal to 4 performance. Videos. http://www.youtube.com/watch?v=7ip-buff-hkq and http://www.youtube.com/watch?v=npfvesbk1qr for his design, and it appears that he is about to go commercial. http://www.inkomp-delta.com/index.html in May 2014. It is shown that an effective device can be constructed from a permanent magnet, a toroid and a laminated iron yoke. The arrangement is displayed like this. When the input coil is pulsed with an input voltage, it causes a flux reversal in the frame around which the output coil is wound, generating an electrical output. There is another forum related to this and the better known meg of Tom Bearden's, which can be found at http://tech.groups.yahoo.com/group/meg_builders/message/1355, where that particular message states that Valery's device can be made to work at frequencies as low as 50 Hz and can use standard laminated iron frame components and produces coefficient of performance figures up to 5.4, that is, the output power is more than 5 times the input power. A demo video is at http://inkomp-delta.com/page10.html but not in English. It may well be that in order to work well, the meg needs a very narrow input coil with an air gap on each side of it, and the same may well apply to Lorentz Zhang's magnetic frame shown earlier in this chapter. The motionless generators of Kelly Cairo Isaoka received U.S. patent 5,926,083, some 2 years before the well-known meg patent of Tom Bearden and his associates. Personally, I find it hard to understand how the meg patent, in the appendix, could have been awarded when the Isaoka patent was already in place. However, here is most of the content of the Isaoka patent. U.S. Patent 5,926,083, July 20, 1999. Inventor, Kelly Cairo Isaoka. Static magnet dynamo for generating electromotive force based on changing flux density of an open magnetic path. Abstract. A static magnet dynamo including at least one permanent magnet having different poles, a first core comprising a soft magnetic material and which couples the different poles of the permanent magnet to form a closed magnetic path, a second core comprising a soft magnetic material which couples to the closed magnetic path via a paramagnetic material to form an open magnetic path, a magnetized coil wound around a portion of the first core where the closed magnetic path is formed, and an induction coil wound around a portion of the second core. A direction of a flux of the closed magnetic path is changed by applying an alternating voltage to the magnetized coil, generating an electromotive force in the induction coil by electromagnetic induction due changes in a flux of the open magnetic path induced by the change in direction of the flux of the closed magnetic path. Field of the invention. This invention relates to a dynamo which generates electromotive force by electromagnetic induction by changing the flux passing through an induction coil. More particularly, this invention relates to a static magnet dynamo that changes magnets that pass through an induction coil without turning the armature or electromagnet. Discussion of background. Dynamos currently in practical use are so designed as to generate electromotive force by electromagnetic induction by changing the flux passing through an induction coil. Dynamos that generate power this way come in A wide variety, ranging from large models used in hydroelectric, thermal or atomic power plants to small models such as small dynamos with a diesel engine. In all dynamo models mentioned above, the armature and electromagnet are turned, to change the flux passing through the induction coil, thus generating electromotive force in the induction coil by electromagnetic induction. For examples, the armature and electromagnet are turned by the torque of a water turbine in hydroelectric power generation, by the torque of the steam turbine in thermal and atomic power generation, and by the torque of the diesel engine in small dynamos. Disadvantages: dynamos that generate electromotive force by electromagnetic induction as mentioned above are so designed that, regardless of the size of the dynamo, the armature and electromagnet are turned in order to change the flux passing the induction coil. These dynamos are disadvantageous in that the said turning of the armature and electromagnet generates vibrations and noise. Objects of the invention. The purpose of this invention is to provide a static magnet dynamo devoid of any torque-giving means or other moving part to eliminate vibrations and noise, in order to resolve the various problems mentioned above. To resolve the above problems, this invention is composed as described below. The static magnet dynamo involved in this invention consists of at least one permanent magnet, a first core consisting of a soft magnetic material forming a closed magnetic path by coupling the different poles of the said permanent magnet, a second core consisting of a soft magnetic material forming an open magnetic path by being coupled to the closed magnetic path via a paramagnetic material, a magnetized coil wound around a part consisting of only the closed magnetic path of the first core, and an induction coil wound around the second core. The point of this invention is to generate electromotive force in the induction coil by electromagnetic induction by changing the direction of the flux of the closed magnetic path by applying an alternating voltage to the magnetized coil and by changing the flux of the open magnetic path induced by changes in the direction of the flux in the closed magnetic path. Effects. In the above configuration, the static magnet dynamo involved in this invention consists of a first core consisting of a permanent magnet and a closed magnetic path, a second core consisting of an open magnetic path via a paramagnetic material, a magnetized coil wound around the part consisting only of the closed magnetic path of the first core, and an induction coil wound around the second magnetic path. The dynamo is so designed as to generate electromotive force in the induction coil by electromagnetic force by changing the direction of the flux of the first core by applying an alternating voltage to the magnetized coil, and by changing the flux of the second core induced by changes in the direction of the flux of the first core. This makes it possible to change the flux passing through the induction coil without a torque-giving means or other moving part and to generate electromotive force in the induction coil by electromagnetic induction, thus enabling power generation without causing vibrations or noise. This dynamo can also be downsized and made available at low prices. Other characteristics and benefits of this invention will be made clear by the description given below with diagrams attached. Brief description of the drawings. A more complete appreciation of the invention and many of the attendant advantages thereof will be readily obtained as the same becomes better understood by reference to the following detailed description when considered in connection with the accompanying drawings, wherein Fig. 1 represents a basic configuration of a static magnet dynamo with an open magnetic path involved in this invention. Fig. 2 represents how a flux in the direction opposed to that of a permanent magnet typically occurs in the magnetized coil. Fig. 3 represents how a flux in the direction opposed to that of a permanent magnet typically disappears from the magnetized coil. Fig. 4 represents how a flux in the same direction as that of the permanent magnet typically occurs in the magnetized coil. Fig. 5 is a first embodiment of the static magnet dynamo involved in this invention. Fig. 6 is a second embodiment of the static magnet dynamo involved in this invention. Fig. 7 is a third embodiment of the static magnet dynamo involved in this invention. Fig. 8 is a fourth embodiment of the static magnet dynamo involved in this invention. Fig. 9 is a fifth embodiment with an open magnetic path. Fig. 10 is a basic configuration of a static magnet dynamo with a closed magnetic path involved in this invention. Fig 11 is a first embodiment of the static magnet dynamo with a closed magnetic path involved in this invention. Description of the preferred embodiments. Referring now to the drawings, wherein like reference numerals designate identical or corresponding parts throughout the several views, and more particularly to Fig 1 where there is illustrated a basic configuration of the static magnet dynamo with one permanent magnet. Figs 2, 3, and 4 describe how the static magnet dynamo represented in Fig 1 generates power. As indicated in the figures, the first core 2 formed to couple the permanent magnet 1 and the different poles of the permanent magnet 1 in an annular manner, forms a closed magnetic path. This closed magnetic path is then equipped with a second core 3 via a paramagnetic material 10 m to 5 mm thick. This results in the formation of an open magnetic path consisting of a permanent magnet 1, part of a first core 2, a paramagnetic material, and a second core 3. The part consisting only of the closed magnetic path of the first core 2 is wound around with a magnetized coil 4. The second core 3 is then wound around with an induction coil 5 designed to generate electromotive force by electromagnetic induction. Here, the permanent magnet 1 is a magnet with a high residual flux density, a great coercive force, and a large maximum energy product for higher power generation efficiency. Typical materials used here are neodymium iron boride magnet, North Dakota 2Fe14B, samarium cobalt magnet, SM2CO17, or samarium iron nitride, small 2Fe17N2. The first core 2 and the second core 3 are made of a soft magnetic material having a high permeability, with high initial, maximum, and other permeability levels, high residual flux density and saturation magnetization, and small coercive force, thus making effective use of the flux of the magnetic path for power generation. Examples include permalloy-based alloys. Applicable paramagnetic materials are those with a specific permeability comparable to that of a vacuum, such as air, copper, and aluminium. When air is used as a paramagnetic material, that is, when a gap G is secured between the first core 2 and the second core 3, the second core 3 is retained with a solid paramagnetic material. The figures represent embodiments with a gap G, without a solid paramagnetic material designed to retain the second core 3. Following is a description of how a static magnet dynamo of the above configuration generates power. First, when no voltage is applied to the magnetized coil 4 of the static magnet dynamo, a first flux 11 is formed in the first core 2 in the direction going from the N pole to the S pole of the permanent magnet 1. In this state, no flux has been formed in the second core 3 coupled viaduct the gap G. A voltage can be applied to the magnetized coil 4 in 3 manners described below. In the first voltage application, as indicated in Fig 2, a DC voltage versus is applied to the magnetized coil 4 in the direction that the voltage repels the first flux 11 of the first core 2 generated by the permanent magnet 1, and vice versa, that is, in such a manner that the second flux 12 occurs in the reverse direction of the first flux 11. As a result, the first flux 11 repels the second flux 12 and vice versa, so that the flux more easily leaks from the closed magnetic path. The first flux 11 and the second flux 12, which more easily leak from the closed magnetic path, jump across the gap G and enter the second core 3, so that a third flux 13 is induced in the second core 3. Furthermore, the induction of this third flux 13 changes the flux passing through the induction coil 5, so that electromotive force V1 occurs in the induction coil 5, resulting in power being generated. Next, removing the DC voltage applied to the magnetized coil 4 prompts the first core 2 to try going back to a state where only the first flux 11 is formed as indicated in Fig 1. At that time, the second core 3 has a flux in the reverse direction of the third flux 13, that is, the fourth flux 14 indicated in Fig 3, in order to kill the third flux 13. Then, the induction of the fourth flux 14 changes the flux passing the induction coil 5, so that electromotive force V2 occurs in the induction coil 5, resulting in power being generated. Power generation in this first voltage application can be realized by a static magnet dynamo involved in this invention, a DC power supply to apply a DC voltage versus to the magnetized coil 4, and a switching circuit that turns the DC power supply on and off. A contactless switching circuit can be made if a semiconductor switching device, such as a thyristor, is available. The second voltage application is the same as the first voltage application up to the point where the third flux 13 is induced in the second core 3 by applying a DC voltage versus to the magnetized coil 4 so as to generate the second flux 12 in the reverse direction of the first flux 11 and where the third flux 13 is induced to generate electromotive force V1 in the induction coil 5, thus generating power. Next, changing the polarity of the DC voltage applied to the magnetized coil 4 generates in the first core 2 the first flux 11 caused by the permanent magnet 1, as well as the fifth flux 15 in the same direction as the first flux caused by the magnetized coil 4. Here, the first flux 11 is given the fifth flux 15, so that the second core 3 is given the fourth flux 14 as indicated in Fig 4, as well as the sixth flux 16 in the same direction as the fourth flux 14. Furthermore, inducing the fourth flux 14 and the sixth flux 16 changes the flux passing through the induction coil 5, so that an electromotive force V3 larger than the electromotive force V2 is generated in the rotary coil to produce power. This second voltage application requires a polarity switching circuit PSC that changes the polarity of due voltage instead of a switching circuit that turns on and off the DC voltage applied to the magnetized coil 4 in the first voltage application. This polarity switching circuit can be made of a semiconductor switching device, similarly to the switching circuit in the first voltage application. In the third voltage application, AC voltage versus is applied to the magnetized coil 4 instead of applying DC voltage to the magnetized coil 4 in the second voltage application with the polarity changed. The flux generated by applying AC voltage to the magnetized coil 4 becomes an alternating flux that alternates between the second flux 12 in Fig 2 and the fifth flux 15 in Fig 4. Then, the flux induced in the second core 3 is the third flux 13 in Fig 2 when the second flux 12 is generated, and is the fourth flux 14 trying to kill the sixth flux 16 and the third flux 19 in Fig 4 when the fifth flux 15 is generated. That is, the flux induced in the second core 3 naturally also becomes an alternating flux. In power generation of this third voltage application, AC voltage is applied to the magnetized coil 4, which overcomes the need for a switching circuit or polarity switching circuit PSC, which was needed in the first and the second voltage application, so that the device becomes simplified. Furthermore, the flux induced in the first core 2 and the second core 3 becomes an alternating flux induced by AC voltage, so that the dynamo functions also as a transformer having a gap G between the first core 2 and the second core 3. It is therefore possible to increase further the electromotive force V generated by electromagnetic induction in the induction coil 5. Next, the power generation efficiency of a static magnet dynamo involved in this invention is described. The static magnet dynamo can be considered as a transformer if its permanent magnet 1 is removed and there is a gap G. A transformer entails an eddy current loss V and hysteresis loss WH of the core, and a loss WR due to the electric resistance of the coil. These factors are in a relation formulated below. Total loss W1 equal V plus WH plus WR. 1. Let the input be Win and the output WO, and the Win becomes equal to the total loss, so that the conversion efficiency of the transformer is EFF equal WO slash Win equal WO, V plus WH plus WR, 1. 2. In reality, in Fig 1, the closed magnetic path consisting of the first core 2 contains a permanent magnet 1. The flux of this permanent magnet 1 therefore contributes to power generation. Therefore, in Fig 1, let the input be WIN2 and the output WO2, then WO2 equal WP plus Win2. 3. Where WP represents power resulting from the flux of the permanent magnet 1 contributing to power generation, and represents a conversion efficiency obtained when the device is considered as a transformer with a gap G. Therefore, power generation efficiency is EFF equal WO2/WIN2 or EFF equal WP/WIN2 plus 4. Here, since 1, that is, if power obtained resulting from the flux of the permanent magnet 1 contributing to power generation is larger than dynamo power supplied to the magnetist coil 4, power generation efficiency becomes no less than 1, so that the device can display its performance as a dynamo. Thus, the inventor examined as described below how much the flux of the permanent magnet 1 contributes to the induction of the third flux 13 in Fig 2. First, the inventor provided static magnet dynamos of the basic configuration indicated in Fig 1, one with a permanent magnet 1 and another without a permanent magnet 1. The inventor then compared the power levels needed to induce fluxes of equal flux densities to the second core 3 of each embodiment, that is, the power levels supplied to the magnetist coil 4. As a result, an embodiment with a permanent magnet 1 required only a very low power level to be supplied to the magnetist coil 4. It was observed that the power level required was no more than 1/40th of that of the embodiment without a permanent magnet 1, depending on the test condition. In a static magnet dynamo involved in this invention, therefore, WIN2 can be made sufficiently smaller than WP, so that the inventor considers it possible to make WP/WIN2 1. Embodiment 1 next, as the first embodiment, a static magnet dynamo system composed of two static magnet dynamos of the basic configuration is described based on Fig 5. In Fig 5a, in a static magnet dynamo, a closed magnetic path is made of two permanent magnets 1 and 2 first cores 2 formed so as to couple the different poles of one permanent magnet 1 with the other permanent magnet 1 in an annular manner. This closed magnetic path is then equipped with a second core 3 via a gap G. This forms an open magnetic path consisting of a permanent magnet 1, part of a first core 2, a paramagnetic material, and a second core 3. This open magnetic path can be arranged in two different ways. In one configuration, as indicated in Fig 5a, one open magnetic path can be made of two permanent magnets 1 and 2 second cores 3. In the other configuration, as indicated in Fig 5b, one open magnetic path can be made of one permanent magnet 1 and another can be made of one first core 2. The static magnet dynamos in Fig 5a and Fig 5b do not differ substantially in terms of effect results, except that their patterns forming such an open magnetic path differ. The part forming only a closed magnetic path of each first core 2 is wound around with a magnetist coil 4. Each second core 3 is then wound around with an induction coil 5 which generates electromotive force by electromagnetic induction. This static magnet dynamo forms a first flux 11 in the first core 2 in the direction going from the N pole to the S pole of the permanent magnet 1, with no voltage applied to the magnetist coil 4. Furthermore, the action of this dynamo applying voltage to the magnetist coil 4 and generating electromotive force in the induction coil 5 by electromagnetic induction to generate power is similar to static magnet dynamos of the basic configuration. The static magnet dynamo with two permanent magnets 1 as mentioned above has well-balanced magnetic paths. Since the flux of the permanent magnets 1 can be effectively used, this embodiment achieves higher power generation efficiency than static magnet dynamos of the basic configuration. The first embodiment is a static magnet dynamo system composed of two static magnet dynamos of the basic configuration. Similarly, a static magnet dynamo system can be made as a combination of three or more static magnet dynamos of the basic configuration, Figs 1 to 4. In that case, similarly to the first embodiment, an open magnetic path can be formed in two manners. One configuration is the formation of one open magnetic path by coupling all permanent magnets 1 with a second core 3. The other is the formation of as many open magnetic paths as permanent magnets by coupling the N pole of each permanent magnet 1 to the S pole with a second core 3. Embodiment 2. Next, the second embodiment of the present invention is represented in Fig 6. The third embodiment in Fig 7. And the fourth embodiment in Fig 8. In these embodiments, the action of applying voltage to the magnetized coil 4 and generating electromotive force in the induction coil 5 by electromagnetic induction is similar to that of a static magnet dynamo of the basic configuration, Figs 1 to 4. The second and the third embodiments represented in Fig 6 and Fig 7 have the same basic configuration as the first embodiment, except that the first core 2 in each embodiment is shaped quite differently. In the second embodiment, the part opposed to the end of the second core 3 sticks out toward the end of the second core 3. Thus, the leakage flux due to the repellence of the first flux 11 and the second flux 12 generated. In the first core 2 jumps across the gap G and enters the second core 3 with greater ease. Embodiment 3. The third embodiment is so designed that the part coupling the second core 3 is that part of the first core 2 which is nearest to the permanent magnet 1 and, to shorten the open magnetic path even further, the two permanent magnets 1 are close to each other. Since a flux tends to form a closed magnetic path with the shortest distance, the leakage flux due to the repellence of the first flux 11 and the second flux 12 generated in the first core 2 jumps across the gap G and enters the second core 3 with greater ease. Embodiment 4. The fourth embodiment indicated in Fig 8, as opposed to a static magnet dynamo of the basic configuration, consists of a first loop where permanent magnets 1 with multiple closed magnetic paths are arranged circularly, with the fluxes oriented in the same direction, and of a second loop which is wound around with a magnetized coil 4 and installed inside the first loop. Furthermore, the parts with their first cores 2 coupling the first loop to the second one stick out toward each other across a specified gap. The parts where this first core 2 stick out are coupled together with a second core 3 via a gap G to form an open magnetic path. This reinforces the flux of the permanent magnets 1 and makes it easier for the leakage flux due to the repellence of the first flux 11 and the second flux 12 generated in the first core 2 to jump across the gap G and enter the second core 3. Embodiment 5. The configuration of a static magnet dynamo involved in this invention has so far been described in terms of embodiments where an open magnetic path is connected to the first core 2 at both ends of the second core 3 via a paramagnetic material. However, this invention is not limited to these embodiments. That is, as indicated in Fig 9, the open magnetic path may be embodied by extending any two parts of the first core 2 in the direction that they approach each other, thus defining them as core extensions 6, and coupling these core extensions 6 via a paramagnetic material 6. This embodiment can be applied to all embodiments mentioned above. Embodiment 6. As indicated in Fig 10, a closed magnetic path consists of a permanent magnet 1 and a first core 2 formed so as to couple the different poles of the said permanent magnet 1 in an annular manner. This closed magnetic path is then equipped with a second core 3 so that it comes magnetically in parallel with the permanent magnet 1, so that a bypass closed magnetic path is composed of a permanent magnet 1, part of a first core 2, and a second core 3. The part consisting only of the closed magnetic path of the first core 2 is wound around with a magnetized coil 4. The second core 3 is then wound around with an induction coil 5 designed to generate electromotive force by electromagnetic induction. The action of a static magnet dynamo of the above configuration generating power is described below. First, when no voltage is applied to the magnetized coil 4 of a static magnet dynamo, the first core 2 forms a first flux 11 in the direction going from the N pole to the S pole of the permanent magnet 1. In this state, a flux similar to that of the first core 2 is generated in the second core 3 as well. Embodiment 7. The seventh embodiment is described below based on Fig 11, in terms of a static magnet dynamo system composed of two static magnet dynamos of the basic configuration and with the relative position of the permanent magnets changed. In a static magnet dynamo, a closed magnetic path is composed of two permanent magnets 1 and two first cores 2 so designed as to couple the different poles of one of the permanent magnets 1 with the other permanent magnet 1 in an annular manner. This closed magnetic path is then equipped with a second core 3. This results in the formation of a bypass closed magnetic path consisting of a permanent magnet 1, part of a first core 2, a paramagnetic material, and a second core 3. The parts where a closed magnetic path of each first core 2 alone is formed are wound around with a magnetized coil 4. Each second core 3 is then wound around with an induction coil 5 designed to generate electromotive force by electromagnetic induction. In this static magnet dynamo, where no voltage is applied to the magnetized coil 4, a first flux 11 is formed in the first core 2 in the direction going from the N pole to the S pole of the permanent magnet 1. The action of applying voltage to the magnetized coil 4 and generating electromotive force in the induction coil 5 by electromagnetic induction to generate power is similar to that of a static magnet dynamo of the basic configuration. In the aforementioned static magnet dynamo incorporating two permanent magnets 1, magnetic paths are arranged in a well-balanced manner. This makes it possible to make effective use of the flux of the permanent magnets 1, so that power generation efficiency is higher than that of a static magnet dynamo of the basic configuration. This invention has so far been described somewhat in detail in terms of the most favorable embodiments. Since it is clear that a wide variety of embodiments can be realized without opposing the philosophy and scope of this invention will not be limited to any particular embodiment, except for the limitations described in the attached claim. Floyd Sweet's VTA generator. Another device in the same category of permanent magnets in conjunction with oscillating coils, was produced by Floyd Sweet. The device was dubbed Vacuum Triode Amplifier or VTA by Tom Bearden. The device was capable of producing more than 500 watts of output power at 120 volts, 60 Hz requiring less than 1/3 of 1 milliwatt as input power. The output power can operate AC motors, lights, heaters and when rectified, DC motors. Thanks is due to Horst Weyrich, who has recently provided me with links to useful material which I had not seen before. This link, http://www.youtube.com/watch?v=0gm9natkyy is to a video in which Floyd shows most of the magnet conditioning process. Recently, some additional information on Floyd Sweet's device has been released publicly by an associate of Floyd's who goes just by his first name of Maurice and who, having reached the age of 70, has decided that it is time to release this additional information. That information can be found in the appendix. I am not aware of anybody who has succeeded in replicating Floyd's VTA, but here is as much information as I have at this time. In the above video, Floyd talks about separating two of his conditioned permanent magnets with an air gap, which is astonishing as he is putting them on opposite sides of a length of aluminium channel with thick walls, and aluminium has a major damping effect on magnetic fields. This arrangement, which seems quite mad, is confirmed by a picture from Floyd's lab. As shown here. This shows clearly that the open ends of the channel are not between the two magnets, allowing an unrestricted magnetic field to flow between them, but instead, two channel thicknesses of aluminium are between the two magnets, obstructing the magnetic flow. Quite remarkable. Floyd shows two coils being used to condition the magnets. The first is the large vertical coil shown here in front of Floyd. The second coil is not seen as it is inside the vertical coil, sitting flat on the base, and consisting of an entire reel of AWG number 17, 1.15 mm diameter, wire, something like this. This coil operates effectively as an air core solenoid, producing a strong axial magnetic field inside the larger coil which surrounds it. This inside coil is driven by a sine wave signal in the 10 Hz to 15 Hz range, boosted through a 100-watt audio amplifier which provides the current needed to impose the sine wave on this low impedance coil without distorting the waveform. The first step is to determine the resonant frequency of each of the two permanent magnets to be used. The ferrite magnets used appear to be about 6x4x 1 inch, 150x100x 25 mm. As they will eventually be used as a pair, one end of each is marked so that they can be aligned in the correct orientation after conditioning. That size of magnet appears to have a resonant frequency of about 12 Hz, but each magnet will be slightly different. The inside, low-frequency coil is powered up at around 12 Hz, the length of the magnet aligned with the Earth's magnetic field, that is, north/south, and placed on top of the vertical coil. An iron shim is used in transformer. Core construction is placed vertically on top of the magnet as an indication of resonating. As shown in the video, the sine wave frequency feeding the AWG number 17 coil is adjusted slowly to find the point at which the iron shim vibrates most strongly. That frequency is noted, and the same is done for the second magnet. It is not likely that the two resonant frequencies will be the same, and so the average frequency for the pair is used. Next, the two magnets are placed in attraction mode, one on each side of the aluminium channel, with their marked ends at the same end of the channel. That is, the north pole face of one will touch the aluminium and the south pole face of the other will touch the aluminium. The two magnets and their separating aluminium channel are then placed inside the main coil and aligned so that the outer north pole faces southwards and the opposite external south pole faces northwards. The large coil dimensions are arranged so that the center of the magnets is at the center of the outer coil. While the inner coil continues to be powered up with a powerful sine wave, the outer coil is now fed a 60 Hz stream of sharp voltage pulses. These are generated by charging up a 16,000 microfarad 250V capacitor and then discharging it through an SCR, thyristor, connected to the outer coil. It is important that the spikes be sharp as they are imposing that frequency on the internal magnetic structure of the magnets. Presumably, if aiming for a European 240V version, then the outer coil would be pulsed at 50 Hz rather than the American 60 Hz and the capacitor would be a 450V rated type. The working pictures of Floyd's prototype powering a load seem to indicate that the one input coil and one output coil as described by Ashley Gray below, are the same as used by Floyd as we see wires coming out of the open end of the channel. Horst wishes to emphasize that it is not easy to make a working replication of Floyd's design as the people at www.highiq.org have tried to replicate it for a number of years now, without any success. Ashley Gray of New Zealand. In April 2014, I was sent some information about a colleague of Floyd Sweet's, Ashley Gray of Nelson, New Zealand. The version described by Ashley appears to be understandable. On June 20, 1994, Ashley says, after a trip to America in 1985 when I was first introduced to Floyd Sweet, I was invited to go back and work with him. At that time he was being funded by Mark Golds of the ESOP Institute, and Daryl Roberts was working as co-coordinator for the Institute in LA. After working with Floyd for some time we left America for England. At that stage the politics had become difficult. While we were in England, we were contacted by Mark Golds and told that Floyd had obtained some results which they would like us to verify for them. On our return to New Zealand, Daryl Roberts sent us the lab notes which he had recorded during the first tests of the space quantum modulator and its construction details. We were asked to repeat the experiments to verify the results. We constructed the device but were unable to get any results at that time. In the light of the new information which had been released, I conducted some further experiments and managed to obtain some interesting results without magnet conditioning which, as far as I was aware, was not used in the original device. The initial device which I constructed when in America, consisted of two 1-inch x 1-inch, 25 x 25 mm, neodymium magnets mounted in a steel frame. There were two modulating windings and one output winding. It was driven by a specially built sine wave oscillator which was adjustable from 1 kHz to 2 kHz. We did not get any output or significant result from this device. Floyd felt that this was due to the high field strength of the neodymium magnets and the closed magnetic path. Floyd did not mention anything about magnet conditioning being necessary. A second prototype was then built, using barium ferrite magnets size 6 inches x 4 inches x 1 inch, 150 x 100 x 25 mm. Ashley appears to be using magnets which are not conditioned. Ashley has had what I consider to be very significant results from his prototype with an output power of 111 watts for an input of just 0.001 watts, a COP of 111,000. Ashley's successful build has an aluminium housing. People get the very mistaken idea that aluminium is not magnetic because magnets do not stick to it. The reality is that aluminium has a really major effect on magnetic fields and can be used as magnetic shielding if thick enough. Ashley's design uses two coils at right angles to each other, and that style of operation can be seen in other free energy designs. Anyway, take a look at the version built by Ashley. The aluminium enclosure is shallow. The ends are 4x25, which is 100x63 mm. The diameter of the input coil is 1.5 inches or 38 mm. Similarly, the output coil length has to be less than 63 mm. The diagram below may give a slightly better idea of the dimensions involved in the construction. At the present time, magnets of that size are available for £14 each in the UK. They each have an 8 kg pull and are very heavy. The magnetic lines of force flow through the length of the output coil and through the width of the input coil. As you can see from the diagram, the unit is compact in spite of the very large magnets. The input needed is a good quality sine wave. Ashley also says, details from lab notes of first successful tests. Original test setup. A signal generator made by WaveTech, USA, was used to drive the input coil. Input coil, 1.5 diameter 120 turns number 20 gauge, 0.812 mm diameter, overall resistance about 1 ohm. Input equals 7.5 volts at 3L microamps equal 23 microwatts. Output coil, 1.5 diameter 12 turns number 12 gauge, 2.05 mm diameter. Output equal 10.4 volts sine wave at 1.84 amps equal 19.15 watts at approximate 400 Hz. Comments. Frequency generally affected resistive 1.8 amp 20 watt bulb load proportionally, brightness increased with frequency, decreased with frequency except at certain points when it appeared inversely related, increasing as frequency decreased, etc. First modifications. The signal generator was replaced with a purpose-built sine wave oscillator of 9-volt output. The input coil was increased to 250 turns of number 18 gauge, 1024 mm, and the output coil was increased to 24 turns of number 18 gauge, 1.024 mm diameter, wire. Magnets, spacing, etc. all remain the same. Input, 7.2 volts at 143 microamps, 0.001 watts. Output, 24.2 volts at 4.6 amps equal 111 watts. Frequency 388 and 402 Hz. Comments. By increasing the area of the wire exposed to or occupying the fluctuating magnetic field, the output was doubled. The exact proportions ratios of the space filling volume of winding to output had not been determined at the time of writing. Magnet size seems to be less important than the volume of the windings, wire diameter, input voltage and current. The current is only limited by the impedance of the wire, which rises dramatically in the magnetic field to several 100,000 ohms, while the impedance when outside the field is only 2 or 3 ohms at 400 Hz. 250 turns number 18, 1 mm diameter, wire. The AC excitation current is only required to support I2R losses, as the magnetic field requires no additional power, as it is not loaded by the wires passing through the field. The unit ran for 10 to 12 hours with no heating occurring, but no longer duration tests were performed. The tests were witnessed by 3 people. Technical notes. The quality of the oscillator is important. There should be no harmonic distortion, i.e. it needs to be a pure sine wave. The signal diode divides the current into the circuit, and being parallel, puts a small microamp current into the power coil as well as the excitation coil. This works with the magnets in such a way that there is produced a vector complementation. When in close proximity to the magnets, the output load bulbs vibrate. The optical generator of Pavel Imres. Pavel was awarded a U.S. patent in the 1970s. The patent is most interesting in that it describes a device which can have an output power which is more than 9 times greater than the input power. He achieves this with a device which has 2 pointed electrodes enclosed in a quartz glass envelope which contains xenon gas under pressure. The higher the pressure, the greater the gain of the device, and a dielectric material. Here, the power supply to one or more standard fluorescent lamps is passed through the device. This produces a power gain which can be spectacular when the gas pressure in the area marked 24 and 25 in the above diagram is high. The patent is included in the set of documents and it contains the following table of experimental measurements. Table 1 shows the data to be obtained relating to the optical electrostatic generator. Table 2 shows the lamp performance and efficiency for each of the tests shown in Table 1. The following is a description of the data in each of the columns of Tables 1 and 2. The results from test number 24, where the gas pressure is a very high 5000 torr, show that the input power for each 40 watt standard fluorescent tubes is 0.9 watts for full lamp output. In other words, each lamp is working to its full specification on less than 1/40th of its rated input power. However, the power taken by the device in that test was 333.4 watts, which with the 90 watts needed to run the 100 lamps, gives a total input electrical power of 423.4 watts instead of the 4000 watts which would have been needed without the device. That is an output power of more than 9 times the input power. From the point of view of any individual lamp, without using this device, it requires 40 watts of electrical input power to give 8.8 watts of light output, which is an efficiency of about 22%, the rest of the input power being converted to heat. In test 24, the input power per lamp is 0.9 watts for the 8.8 watts of light produced, which is a lamp efficiency of more than 900%. The lamp used to need 40 watts of input power to perform correctly. With this device in the circuit, each lamp only needs 0.9 watts of input power, which is only 2.25% of the original power. Quite an impressive performance for so simple a device. The Michel Mayer and Yves Mace isotopic generator. There is a French patent application number FR 2680613 dated August 19, 1991, entitled Activateur pour mutation isotopique, which provides some very interesting information. The system described is a self-contained solid-state energy converter which abstracts large amounts of energy from an ordinary iron bar. This is also shown in Michel's Czechoslovakia patent number 284333. The inventors describes the technique as an isotopic mutation effect, as it converts ordinary iron, isotope 56, to isotope 54 iron, releasing large amounts of electrical energy in the process. This excess energy can, they say, be used to drive inverters, motors or generators. The description of the mechanism which is being used by the device is, the present invention uses a physical phenomenon to which we draw attention and which we will call isotopic change. The physical principle applies to isotope 56 iron, which contains 26 protons, 26 electrons and 30 neutrons, giving a total mass of 56.52 MeV, although its actual mass is 55.80 MeV. The difference between the total mass and the actual mass is therefore 0.72 MeV, this which corresponds to an energy of cohesion per nucleon of 0.012857 MeV. So, if one introduces an additional 105 eV of energy to the iron core isotope 56, that core isotope will have a cohesion energy level of 0.012962 MeV per nucleon, corresponding to iron isotope 54. The instability created by this contribution of energy will transfer the isotope 56 iron to isotope 54, causing a release of 2 neutrons. This process generates an excess energy of 20,000 F since the iron isotope 54 is only 0.70 MeV while isotope 56 has 0.72 MeV. To bring about this iron isotope 56 conversion, we use the principle of nuclear magnetic resonance. The practical method for doing this is by using 3 coils of wire and a magnetic path closing support frame of iron as shown in this diagram. In this arrangement, Coil 1 produces 0.5 Tesla when fed with DC, converting the iron bar into an electromagnet. Coil 2 produces 10 millitesla when fed with a 21 MHz AC sine wave signal. Coil 3 is the output coil, providing 110, 220 or 380 volts AC at about 400 Hz depending on the number of turns in the coil. This simple and cheap system has the potential for producing substantial energy output for a very long time. The inventors claim that this device can be wired to be self-powered, while still powering external devices. Coil 1 turns the iron rod into an electromagnet with its flux channeled in a loop by the iron yoke. Coil 2 then oscillates that magnetic field in resonance with the isotope 56 iron atoms in the rod, and this produces the isotope conversion and release of excess energy. Coil 3 is wound to produce a convenient output voltage. The Coleman/Sedengili SPI generator. This device, patented by Harold Coleman and Ronald Sedengili on December 5, 1956, is quite remarkable. It is a tiny lightweight device which can produce electricity using a self-powered electromagnet and chemical salts. The working life of the device before needing refurbishment is estimated at some 70 years with an output of about 1 kilowatt. The operation is controlled by a transmitter which bombards the chemical sample with 300 MHz radio waves. This produces radioactive emissions from the chemical mixture for a period of 1 hour maximum, so the transmitter needs to be run for 15 to 30 seconds once every hour. The chemical mixture is shielded by a lead screen to prevent harmful radiation reaching the user. The patent, Gigabyte 763062, is included in the appendix. This generator unit includes a magnet, a tube containing a chemical mixture of elements whose nuclei becomes unstable as a result of bombardment by short waves so that the elements become radioactive and release electrical energy, the mixture being mounted between, and in contact with, a pair of different metals such as copper and zinc, and a capacitor mounted between those metals. The mixture is preferably composed of the elements cadmium, phosphorus and cobalt having atomic weights of 112, 31 and 59 respectively. The mixture, which may be of powdered form, is mounted in a tube of non-conducting, high heat resistivity material and is compressed between granulated zinc at one end of the tube and granulated copper at the other end, the ends of the tube being closed by brass caps and the tube being carried in a suitable cradle so that it is located between the poles of a magnet. The magnet is preferably an electromagnet and is energized by the current produced by the unit. The transmitter unit which is used for activating the generator unit may be of any conventional type operating on ultra-short wave and is preferably crystal controlled at the desired frequency. The transmitter unit is of any suitable conventional type for producing ultra-short waves and may be crystal controlled to ensure that it operates at the desired frequency without needing tuning. The quartz tube containing the chemical mixture works best if made up of a number of small cells in series. In other words, considering the cartridge from one end to the other, at one end and in contact with the brass cap, there would be a layer of powdered copper, then a layer of the chemical mixture, then a layer of powdered zinc, a layer of powdered copper, etc. with a layer of powdered zinc in contact with the brass cap at the other end of the cartridge. With a cartridge some 45 mm long and 5 mm diameter, some 14 cells may be included. The devices of Don Smith. Donald Lee Smith died a few years ago. He is famous for his high-power self-powered free energy designs. There are several videos on the web, showing some of his lectures. He produced one PDF document which is shown at the end of this chapter, and in May 2004 he was granted one patent. Don stated clearly in one of his lectures, that he never did disclose the full details of his designs. However, Don says that he discloses enough for somebody who is experienced in radio frequency electronics to be able to deduce the things which he does not disclose and so build a device for his own use. If that is the case, then anybody who has succeeded in doing so has kept very quiet about it afterwards, which would be understandable. Don produced at least 48 different devices which draw energy from what Don prefers to call the ambient background. His devices are capable of supplying kilowatts of excess energy, and in most cases they do not require any input energy to be supplied by the user. Don's work is subtle and not easy to replicate. It is based on the principle that the power output of a circuit increases with the square of the frequency and the square of the voltage. So, if you double the frequency and double the voltage, then the output power goes up and becomes 16 times greater. As a result of this, Don's best-known design uses a neon sign transformer circuit which raises the frequency to around 35,000 cycles per second and raises the voltage to anything from 2,000 volts to 12,000 volts, giving a power output is physically quite small, and yet it has an output of 160 kilowatts, 8,000 volts at 20 amps, from an input of 12 volts 1 amp. That is, the output power is more than 13,000 times greater than the input power. Consequently, his designs are dangerous and can kill you instantly. In other words, his designs are for experienced developers only. Please bear in mind that the voltages here and their associated power levels are literally lethal and perfectly capable of killing anyone who handles the device carelessly when it is powered up. When a replication of this device is ready for routine use, it must be encased so that none of the high voltage connections can be touched by anyone. This is not a suggestion, but it is a mandatory requirement, despite the fact that the components shown in the photographs are laid out in what would be a most dangerous fashion were the circuit to be powered up as it stands. Under no circumstances, construct and test the circuit unless you are already experienced in the use of high voltage circuits or can be supervised by somebody who is experienced in this field. This is a one hand in the pocket at all times type of circuit, and it needs to be treated with great care and respect at all times, so be sensible. Don Smith considered himself to be self-taught. Don says that his understanding comes from the work of Nikola Tesla as recorded in Thomas E. Martin's book The Inventions, Researches, and Writings of Nikola Tesla, ISBN 0-7873-05820. This book can be downloaded from http://www.free-energyinfo.com/teslabook.pdf as a PDF file. Don states that he repeated each of the experiments found in the book, and that gave him his understanding of what he prefers to describe as the ambient background energy, which is also called the zero-point energy field. Don remarks that he advanced further than Tesla in this field, partly because of the devices now available to him and which were not available when Tesla was alive. Don stresses two key points. Firstly, a dipole can cause a disturbance in the magnetic component of the ambient background, and that imbalance allows you to collect large amounts of electrical power, using capacitors and inductors, coils. Secondly, you can pick up as many powerful electrical outputs as you want from that one magnetic disturbance, without depleting the magnetic disturbance in any way. This allows massively more power output than the small power needed to create the magnetic disturbance in the first place. This is what produces a coefficient of performance 1 device, and Don has created nearly 50 different devices based on that understanding. Although they get removed quite frequently, there is one video which is definitely worth watching if it is still there. It is located at http://www.metacafé.com/watch/28205331/don_smith_free_energy and was recorded in 2006. It covers a good deal of what Don has done. In the video, reference is made to Don's website, but you will find that it has been taken over by Big Oil, who have filled it with innocuous similar sounding things of no consequence, apparently intended to confuse newcomers searching for information on Don's designs. The present situation in 2019 is that few people understand Don's designs fully, and I myself fall into that category. The high voltage components are expensive and hard to find, and the high voltages are dangerous. However, we will look at 3 of his many designs and try to understand them as best we can. We will start with his patented design. Patent NL02000035A May 20, 2004. Inventor, Donald Lee Smith. Transformer generator magnetic resonance into electric energy. Abstract. The present invention refers to an electromagnetic dipole device and method, where wasted radiated energy is transformed into useful energy. A dipole as seen in antenna systems is adapted for use with capacitor plates in such a way that the heaviside current component becomes a useful source of electrical energy. Description. Technical field. This invention relates to loaded dipole antenna systems and their electromagnetic radiation. When used as a transformer with an appropriate energy collector system, it becomes a transformer/generator. The invention collects and converts energy which is radiated and wasted by conventional devices. Background art. A search of the International Patent Database for closely related methods did not reveal any prior art with an interest in conserving radiated and wasted magnetic waves as useful energy. Disclosure of the invention. The invention is a new and useful departure from transformer generator construction, such that radiated and wasted magnetic energy changes into useful electrical energy. Gauss meters show that much energy from conventional electromagnetic devices is radiated into the ambient background and wasted. In the case of conventional transformer generators, a radical change in the physical construction allows better access to the energy available. It is found that creating a dipole and inserting capacitor plates at right angles to the current flow allows magnetic waves to change back into useful electrical, coulombs, energy. Magnetic waves passing through the capacitor plates do not degrade and the full impact of the available energy is accessed. 1, or as many sets of capacitor plates as is desired, may be used. Each set makes an exact copy of the full force and effect of the energy present in the magnetic waves. The originating source is not depleted or degraded as is common in conventional transformers. Brief description of the drawings. The dipole at right angles allows the magnetic flux surrounding it to intercept the capacitor plate, or plates, at right angles. The electrons present are spun such that the electrical component of each electron is collected by the capacitor plates. Essential parts are the south and north component of an active dipole. Examples presented here exist as fully functional prototypes and were engineer constructed and fully tested in use by the inventor. In each of the 3 examples shown in the drawings, corresponding parts are used. Fig 1 is a view of the method, where N is the north and S is the south component of the dipole. Here, 1 marks the dipole with its north and south components. 2 is a resonant high-voltage induction coil. 3 indicates the position of the electromagnetic wave emission from the dipole. 4 indicates the position and flow direction of the corresponding heaviside current component of the energy flow caused by the induction coil. 2. 5 is the dielectric separator for the capacitor plate. 7. 6 for the purposes of this drawing, indicates a virtual limit for the scope of the electromagnetic wave energy. In Fig 2a1 is the hole in the capacitor plates through which the dipole is inserted, and in Fig 2b it is the dipole with its north and south poles shown. 2 is the resonant high-voltage induction coil surrounding part of the dipole. 1. The dielectric separator. 5 is a thin sheet of plastic placed between the 2 capacitor plates. 7, the upper plate being made of aluminium and the lower plate made of copper. Unit 8 is a deep cycle battery system powering a DC inverter. 9 which produces 120 volts at 60 Hz, the US main supply voltage and frequency. Obviously, a 240 volt 50 Hz inverter could be used here just as easily, which is used to power whatever equipment is to be driven by the device. The reference number 10 just indicates connecting wires. Unit 11 is a high-voltage generating device such as a neon transformer with its oscillating power supply. Fig 3 is a proof of principle device using a plasma tube as an active dipole. In this drawing, 5 is the plastic sheet dielectric separator of the two plates 7 of the capacitor, the upper plate being aluminium and the lower plate copper. The connecting wires are marked 10 and the plasma tube is designated 15. The plasma tube is 4 feet long, 1.22 m, and 6 inches, 100 mm, in diameter. The high voltage energy source for the active plasma dipole is marked 16 and there is a connector box 17 shown as that is a convenient method of connecting to the capacitor plates when running tests on the device. Fig 4 shows a manufacturer's prototype, constructed and fully tested. 1 is a metal dipole rod and 2 the resonant high voltage induction coil, connected through wires 10 to connector block 17 which facilitates the connection of its high voltage power supply. Clamps 18 hold the upper edge of the capacitor packet in place and 19 is the base plate with its supporting brackets which hold the whole device in place. 20 is a housing which contains the capacitor plates and 21 is the point at which the power output from the capacitor plates is drawn off and fed to the DC inverter. Best method of carrying out the invention. The invention is applicable to any and all electrical energy requirements. The small size and its high efficiency make it an attractive option, especially for remote areas, homes, office buildings, factories, shopping centers, public places, transportation, water systems, electric trains, boats, ships and all things great and small. The construction materials are commonly available and only moderate skill levels are needed to make the device. Claims. 1. Radiated magnetic flux from the dipole, when intercepted by capacitor plates at right angles, changes into useful electrical energy. 2. A device and method for converting for use, normally wasted electromagnetic energy. 3. The dipole of the invention is any resonating substance such as metal rods, coils and plasma tubes which have interacting positive and negative components. 4. The resulting heaviside current component is changed to useful electrical energy. This patent does not make it clear that the device needs to be tuned and that the tuning is related to its physical location on Earth. The tuning will be accomplished by applying a variable frequency input signal to the neon transformer and adjusting that input frequency to give the maximum output. The second of Don's devices to consider is his tabletop very high power generator. This is effectively a Tesla coil system and so the normal electromagnetic effect of the ratio of the number of coil turns does not determine the effect between the coils. The demonstration device looks like this. This device is not the easiest thing in the world to understand. Here is the circuit diagram. It is probably worth mentioning some of the main points which Don Smith appears to be making. There are some very important points being made here, and grasping these may make a considerable difference to our ability to tap into the excess energy available in our local environment. There are 4 points worth mentioning. 1. Voltage. 2. Frequency. 3. Magnetic/electric relationship. 4. Resonance. 1. Voltage. We tend to view things with an intuitive view, generally based on fairly simple concepts. For example, we automatically think that it is more difficult to pick up a heavy object than to pick up a light one. How much more difficult? Well, if it is twice as heavy, it would probably be about twice as much effort to pick it up. This view has developed from our experience of things which we have done in the past, rather than on any mathematical calculation or formula. Well, how about pulsing an electronic system with a voltage? How would the output power of a system be affected by increasing the voltage? Our initial off-the-cuff reaction might be that the power output might be increased a bit, but then hold on, we've just remembered that watts equal volts x amps, so if you double the voltage, then you would double the power in watts. So we might settle for the notion that if we doubled the voltage then we could double the output power. If we thought that, then we would be wrong. Don Smith points out that as capacitors and coils store energy, if they are involved in the circuit, then the output power is proportional to the square of the voltage used. Double the voltage, and the output power is 4 times greater. Use 3 times the voltage and the output power is 9 times greater. Use 10 times the voltage and the output power is 100 times greater. Don says that the energy stored, multiplied by the cycles per second, is the energy being pumped by the system. Capacitors and inductors, coils, temporarily store electrons, and their performance is given by capacitor formula, W equals 0.5 x C x V2 x Hz, where W is the energy in joules, joules equal volts x amps x seconds. C is the capacitance in farads. V is the voltage. Hertz is the cycles per second. Inductor formula, W equals 0.5 x L x A2 x Hz, where W is the energy in joules. L is the inductance in henries. A is the current in amps. Hertz is the frequency in cycles per second. You will notice that where inductors, coils, are involved, then the output power goes up with the square of the current. Double the voltage and double the current gives 4 times the power output due to the increased voltage, and that increased output is increased by a further 4 times due to the increased current, giving 16 times the output power. 2. Frequency. You will notice from the formulas above, that the output power is directly proportional to the frequency Hertz. The frequency is the number of cycles per second, or pulses per second, applied to the circuit. This is something which is not intuitive for most people. If you double the rate of pulsing, then you double the power output. When this sinks in, you suddenly see why Nikola Tesla tended to use millions of volts and millions of pulses per second. However, Don Smith states that when a circuit is at its point of resonance, resistance in the circuit drops to zero and the circuit becomes effectively a superconductor. The energy for such a system which is in resonance is resonance circuit, W equals 0.5 x C x V2 x Hertz, 2, where W is the energy in joules. C is the capacitance in farads. V is the voltage. Hertz is the cycles per second. If this is correct, then raising the frequency in a resonating circuit has a massive effect on the power output of the device. The question then arises, why is the mains power in Europe just 50 cycles per second and in America just 60 cycles per second? If power goes up with frequency, then why not feed households at 1,000,000 cycles per second? One major reason is that it is not easy to make electric motors which can be driven with power delivered at that frequency, so a more suitable frequency is chosen in order to suit the motors in vacuum cleaners, washing machines and other household equipment. However, if we want to extract energy from the environment, then we should go for high voltage and high frequency. Then, when high power has been extracted, if we want a low frequency suited to electric motors, we can pulse the already captured power at that low frequency. It might be speculated that if a device is being driven with sharp pulses which have a very sharply rising leading edge, that the effective frequency of the pulsing is actually determined by the speed of that rising edge, rather than the rate at which the pulses are actually generated. For example, if pulses are being generated at, say, 50 kHz but the pulses have a leading edge which would be suited to a 200 kHz pulse train, then the device might well see the signal as a 200 kHz signal with a 25% mark/space ratio, the very suddenness of the applied voltage having a magnetic shocking effect equivalent to a 200 kHz pulse train. 3. Magnetic/electric relationship. Don states that the reason why our present power systems are so inefficient is because we concentrate on the electric component of electromagnetism. These systems are always 1 Colombian peso, as electricity is the losses of electromagnetic power. Instead, if you concentrate on the magnetic component, then there is no limit on the electric power which can be extracted from that magnetic component. Contrary to what you might expect, if you install a pickup system which extracts electrical energy from the magnetic component, You can install any number of other identical PIC UPS, each of which extract the same amount of electrical energy from the magnetic input, without loading the magnetic wave in any way. Unlimited electrical output for the cost of creating a single magnetic effect. The magnetic effect which we want to create is a ripple in the zero-point energy field, and ideally, we want to create that effect while using very little power. Creating a dipole with a battery which has a plus and a minus terminal or a magnet which has north and south poles, is an easy way to create an electromagnetic imbalance in the local environment. Pulsing a coil is probably an even better way, as the magnetic field reverses rapidly if it is an air core coil, such as a Tesla coil. Using a ferromagnetic core to the coil can create a problem, as iron can't reverse its magnetic alignment very rapidly, and ideally, you want pulsing which is at least 1,000 times faster than iron can handle. Don draws attention to the transmitter/receiver. Educational Kit Resonance Circuits number 10, 416, which was supplied by the Science Source, Maine. This kit demonstrated the generation of resonant energy and its collection with a receiver circuit. However, if several receiver circuits are used, then the energy collected is increased several times without any increase in the transmitted energy. This is similar to a radio transmitter where hundreds of thousands of radio receivers can receive the transmitted signal without loading the transmitter in any way. In Don's day, this kit was driven by a 1.5 volt battery and lit a 60 watt bulb which was supplied. Not surprisingly, that kit has been discontinued and a trivial kit substituted. If you get the Science Source Educational Kit, then there are some details which you need to watch out for. The unit has two very nice quality plastic bases and two very neatly wound coils, each of 60 turns of 0.47 mm diameter enameled copper wire on clear acrylic tubes 57 mm, 225, in diameter. The winding covers a 28 mm section of the tube. The layout of the transmitter and receiver modules does not match the accompanying instruction sheet, and so considerable care needs to be taken when wiring up any of their circuits. The circuit diagrams are not shown, just a wiring diagram, which is not great from an educational point of view. The one relevant circuit is: before you buy the kit, it is not mentioned that in order to use it, you now need a signal generator capable of producing a 10-volt signal at 1 MHz. The coil has a DC resistance of just 1.9 ohms, but at a 1 MHz resonant frequency, the necessary drive power is quite low. A variable capacitor is mounted on the receiver coil tube, but the one in my kit made absolutely no difference to the frequency tuning, nor was my capacitance meter able to determine any capacitance value for it at all, even though it had no trouble at all in measuring the 101 pF capacitor, which was exactly the capacitance printed on it. For that reason, it is shown in blue in the circuit diagram above. Disconnecting it made no difference whatsoever. In this particular kit, standard screw connectors have had one screw replaced with an Allen key-headed bolt which has a head large enough to allow finger tightening. Unfortunately, those bolts have a square cut tip where a dome tip is essential if small diameter wires are to be clamped securely. If you get the kit, then I suggest that you replace the connectors with a standard electrical screw connector strip. In tests, the LED lights up when the coils are aligned and within about 100 mm of each other, or if they are close together side by side. This immediately makes the Hubbard device spring to mind. Hubbard has a central electromagnetic transmitter surrounded by a ring of receivers closely coupled magnetically to the transmitter, each of which will receive a copy of the energy sent by the transmitter. Don points to an even more clearly demonstrated occurrence of this effect in the Tesla coil. In a typical Tesla coil, the primary coil is much larger diameter than the inner secondary coil. If, for example, 8000 volts is applied to the primary coil, which has 4 turns, then each turn would have 2000 volts of potential. Each turn of the primary coil transfers electromagnetic flux to every single turn of the secondary winding, and the secondary coil has a very large number of turns. Massively more power is produced in the secondary coil than was used to energize the primary coil. A common mistake is to believe that a Tesla coil can't produce serious amperage. If the primary coil is positioned in the middle of the secondary coil as shown, then the amperage generated will be as large as the voltage generated. A low power input to the primary coil can produce kilowatts of usable electrical power. 4. Resonance. An important factor in circuits aimed at tapping external energy is resonance. It can be hard to see where this comes in when it is an electronic circuit which is being considered. However, everything has its own resonant frequency, whether it is a coil or any other electronic component. When components are connected together to form a circuit, the circuit has an overall resonant frequency. As a simple example, consider a swing. If the swing is pushed before it reaches the highest point on the mother's side, then the push actually opposes the swinging action. The time of one full swing is the resonant frequency of the swing, and that is determined by the length of the supporting ropes holding the seat and not the weight of the child nor the power with which the child is pushed. Provided that the timing is exactly right, a very small push can get a swing moving in a substantial arc. The key factor is matching the pulses applied to the swing, that is, to the resonant frequency of the swing. Get it right and a large movement is produced. Get it wrong, and the swing doesn't get going at all, at which point, critics would say see swings just don't work, this proves it. This principle is demonstrated in the video at http://www.youtube.com/watch?v=IR week 1 VFOIOA. Establishing the exact pulsing rate needed for a resonant circuit is not particularly easy, because the circuit contains coils, which have inductance, capacitance and resistance, capacitors, which have capacitance and a small amount of resistance, and resistors and wires, both of which have resistance and some capacitance. These kinds of circuit are called LRC circuits because L is the symbol used for inductance, R is the symbol used for resistance and C is the symbol used for capacitance. Don Smith provides instructions for winding and using the type of air core coils needed for a Tesla coil. He says: 1. Decide a frequency and bear in mind the economy of the size of construction selected. The factors are: A. Use radio frequency, above 20 kHz. B. Use natural frequency, i.e. match the coil wire length to the frequency, coils have both capacitance and inductance. C. Make the wire length either 1/4, 1/2 of the full wavelength. D. Calculate the wire length in feet as follows. If using 1/4 wavelength, then divide 247 by the frequency in megahertz. If using 1/2 wavelength, then divide 494 by the frequency in megahertz. If using the full wavelength, then divide 998 by the frequency in megahertz. For wire lengths in meters. If using 1/4 wavelength, then divide 75.29 by the frequency in megahertz. If using 1/2 wavelength, then divide 150.57 by the frequency in megahertz. If using the full wavelength, then divide 304.19 by the frequency in megahertz. 2. Choose the number of turns to be used in the coil when winding it using the wire length just calculated. The number of turns will be governed by the diameter of the tube on which the coil is to be wound. Remember that the ratio of the number of turns in the L1 and L2 coils controls the overall output voltage. For example, if the voltage applied the large outer coil L1 is 2400 volts and L1 has 10 turns, then each turn of L1 will have 240 volts dropped across it. This 240 volts of magnetic induction transfers 240 volts of electricity to every turn of wire in the inner L2 coil. If the diameter of L2 is small enough to have 100 turns, then the voltage produced will be 24,000 volts. If the diameter of the L2 former allows 500 turns, then the output voltage will be 120,000 volts. 3. Choose the length and diameter of the coils. The larger the diameter of the coil, the fewer turns can be made with the wire length and so the coil length will be less, and the output voltage will be lower. 4. For example, if 24.7 MHz is the desired output frequency, then the length of wire, in feet, would be 247 divided by 24.7, which is 10 feet of wire, 3048 mm. The coil may be wound on a standard size of PVC pipe, or alternatively, it can be purchased from a supplier, typically, an amateur radio supply store. If the voltage on each turn of L1 is arranged to be 24 volts and the desired output voltage 640 volts, then there needs to be 640/24 equal 26.66 turns on L2, wound with the 10 feet of wire already calculated. PJK, at this point, Don's calculations go adrift and he suggests winding 30 turns on a 2-inch former. If you do that, then it will take about 16 feet of wire and the resonant point at 10 feet will be at about 19 turns, giving an output voltage of 458 volts instead of the required 640 volts, unless the number of turns on L1 is reduced to give more than 24 volts per turn. However, the actual required diameter of the coil former, plus 1 diameter of the wire, is 10x12/26.67 x 3.14159, equal 1.43 inches. You can make the size of former up quite easily if you want to stay with 10 turns on the L1 coil. 5. Connect to the start of the coil. To determine the exact resonant point on the coil, a measurement is made. Off-the-shelf multimeters are not responsive to high-frequency signals, so a cheap neon is used instead. Holding one wire of the neon in one hand and running the other neon wire along the outside of the L2 winding, the point of brightest light is located. Then the neon is moved along that turn to find the brightest point along that turn, and when it is located, a connection is made to the winding at that exact point. L2 is now a resonant winding. It is possible to increase the Q effectiveness of the coil by spreading the turns out a bit instead of positioning them so that each turn touches both of the adjacent turns. 6. The input power has been suggested as 2400 volts. This can be constructed from a Jacob's ladder arrangement or any step-up voltage system. An off-the-shelf module as used with lasers is another option. 7. Construction of the L1 input coil has been suggested as having 10 turns. The length of the wire in this coil is not critical. If a 2-inch diameter PVC pipe was used for the L2 coil, then the next larger size of PVC pipe can be used for the L1 coil former. Cut a 10-turn length of the pipe, probably a 3-inch diameter pipe. The pipe length will depend on the diameter of the insulated wire used to make the winding. Use a good quality multimeter or a specialized LCR meter to measure the capacitance, in farads, and the inductance, in henries, of the L2 coil. Now, put a capacitor for matching L1 to L2 across the voltage input of L1, and a spark gap connected in parallel is required for the return voltage from L1. A trimmer capacitor for L1 is desirable. 8. The performance of L2 can be further enhanced by attaching an earth connection to the base of the coil. The maximum output voltage will be between the ends of coil L2 and lesser voltages can be taken off intermediate points along the coil if that is desirable. This frequency information can be rather hard to understand in the way that Don states it. It may be easier to follow the description given by one developer who says, "I have noticed that any machine can be made a super machine just by adding a bipolar capacitor across the coil. Nothing else is needed. With the correct capacitor the coil becomes naturally resonant and uses very little amperage. Each machine uses a different size capacitor. The correct capacitor size can be calculated by dividing the speed of light by the coil's wire length first to get the coil's natural frequency and then dividing the voltage to be used by that frequency. The result is the correct size for the capacitor. Your machine will then be very powerful even working from a 12V car battery, no other additions needed. My coil's wire length is 497.333 meters. 299 million m/sec/497.333 m equals 600,000 Hz. 12 V/600,000 equals 0.00002 or 20 microfarads. A beautiful naturally resonant tank circuit. You can use this with any coil for over unity. Once we have a naturally resonant coil/capacitor combination, we can bring the frequency down to 50 Hz by calculating for the power factor correction. Hertz equal resistance x farads, then 50 Hz equal Rx 0.00002. So 50/0.00002 equal 2500000, and R equal 2500000 or 2.5 megohms. We then place all three components in parallel and our coil should give us a 50 Hz output. Don provides quite an amount of information on one of his devices shown here. Without his description of the device, it would be difficult to understand its construction and method of operation. As I understand it, the circuit of what is mounted on this board is as shown here. This arrangement has bothered some readers recently, as they feel that the spark gap should be in series with the L1 coil, like this. This is understandable, as there is always a tendency to think of the spark gap as being a device which is there to protect against excessive voltages rather than seeing it as an active component of the circuit, a component which is in continuous use. In 1925, Hermann Plausen was granted a patent for a whole series of methods for converting the high voltage produced by a tall aerial system into usable, standard electricity. Hermann starts off by explaining how high voltage can be converted into a convenient form, and he uses a Wimshurst static electricity generator as an example of a constant source of high voltage. The output from a rectified Tesla coil, a Wimshurst machine and a tall aerial are very much alike, and so Hermann's comments are very relevant here. He shows it like this. Here, the output of the Wimshurst machine is stored in two high-voltage capacitors, Leyden jars, causing a very high voltage to be created across those capacitors. When the voltage is high enough, a spark jumps across the spark gap, causing a massive surge of current through the primary winding of the transformer, which in his case is a step-down transformer, as he is aimed at getting a lower output voltage. Don's circuit is almost identical. Here the high voltage comes from the battery/inverter/neon tube driver/rectifiers, rather than from a mechanically driven Wimshurst machine. He has the same build-up of voltage in a capacitor with a spark gap across the capacitor. The spark gap will fire when the capacitor voltage reaches its designed level. The only difference is in the positioning of the capacitor, which, if it matched Hermann's arrangement exactly, would be like this. Which would be a perfectly viable arrangement as far as I can see. You will remember that Tesla, who always speaks very highly of the energy released by the very sharp discharge produced by a spark, shows a high voltage source feeding a capacitor with the energy passing through a spark gap to the primary winding of a transformer. However, with Don's arrangement, it can be a little difficult to see why the capacitor is not short-circuited by the very low resistance of the few turns of thick wire forming the L1 coil. Well, it would do that if we were operating with DC, but we are most definitely not doing that, as the output from the neon tube driver circuit is pulsing 35,000 times per second. This causes the DC resistance of the L1 coil to be of almost no consequence, and instead, the coil's impedance or reactance, effectively, its AC resistance, is what counts. Actually, the capacitor and the L1 coil being connected across each other have a combined reactance or resistance to pulsing current at this frequency. This is where the nomograph diagram comes into play, and there is a much easier to understand version of it a few pages later on in this document. So, because of the high pulsing frequency, the L1 coil does not short-circuit the capacitor, and if the pulsing frequency matches the resonant frequency of the L1 coil, or a harmonic of that frequency, then the L1 coil will actually have a very high resistance to current flow through it. This is how a crystal set radio receiver tunes in a particular radio station, broadcasting on its own frequency. Anyway, Coming back to Don's device shown in the photograph above, the electrical drive is from a 12-volt battery which is not seen in the photograph. Interestingly, Don remarks that if the length of the wires connecting the battery to the inverter are exactly 1/4 of the wavelength of the frequency of the oscillating magnetic field generated by the circuit, then the current induced in the battery wires will recharge the battery continuously, even if the battery is supplying power to the circuit at the same time. The battery supplies a small current through a protecting diode, to a standard off-the-shelf true sine wave inverter. An inverter is a device which produces mains voltage alternating current from a DC battery. As Don wants adjustable voltage, he feeds the output from the inverter into a variable transformer called a variac, although this is often made as part of the neon driver circuit to allow the brightness of the neon tube to be adjusted by the user. This arrangement produces an AC output voltage which is adjustable from 0 volts up to the full mains voltage, or a little higher, though Don does not want to use a higher voltage. The use of this kind of adjustment usually makes it essential for the inverter to be a true sine wave type. As the power requirement of the neon tube driver circuit is so low, the inverter should not cost very much. The neon tube driver circuit is a standard off-the-shelf device used to drive neon tube displays for commercial establishments. The one used by Don contains an oscillator and a step-up transformer, which together produce an alternating current of 9,000 volts at a frequency of 35,100 Hz, sometimes written as 35.1 kHz. The term Hz stands for cycles per second. Don lowers the 9,000 volts as he gets great power output at lower input voltages, and the cost of the output capacitors is a significant factor. The particular neon tube driver circuit which Don is using here, has two separate outputs out of phase with each other, so Don connects them together and uses a blocking diode in each line to prevent either of them affecting the other one. Not easily seen in the photograph, the high voltage output line has a very small, encapsulated, gas discharge tube spark gap in it, and the line is also earthed. The device looks like this. Please note that when an earth connection is mentioned in connection with Don Smith's devices, we are talking about an actual wire connection to a metal object physically buried in the ground, whether it is a long copper rod driven into the ground, or an old car radiator buried in a hole like Tyrrell Copenhagen's uses. When Thomas Henry Moray performed his requested demonstration deep in the countryside at a location chosen by the skeptics, the light bulbs which formed his demonstration electrical load, glowed more brightly with each hammer stroke as a length of gas pipe was hammered into the ground to form his earth connection. It should be remarked that since Don purchased his neon tube driver module, that newer designs have generally taken over completely, especially in Europe, and these designs have built-in earth leakage current protection which instantly disables the circuit if any current is detected leaking to ground. This feature makes the unit completely unsuitable for use in a Don Smith circuit because the transfer of current to the ground is wholly intentional and vital for the operation of the circuit. The output of the neon tube driver circuit is used to drive the primary L1 winding of a Tesla coil-style transformer. This looks ever so simple and straightforward, but there are some subtle details which need to be considered. The operating frequency of 35.1 kHz is set and maintained by the neon tube driver circuitry, and so, in theory, we do not have to do any direct tuning ourselves. However, we want the resonant frequency of the L1 coil and the capacitor across it to match the neon driver circuit frequency. The frequency of the L1 coil winding will induce exactly the same frequency in the L2 secondary winding. However, we need to pay special attention to the ratio of the wire lengths of the two coil windings, as we want these two windings to resonate together. A rule of thumb followed by most Tesla coil builders is to have the same weight of copper in the L1 and L2 coils, which means that the wire of the L1 coil is usually much thicker than the wire of the L2 coil. If the L1 coil is to be 1/4 of the length of the L2 coil, then we would expect the cross-sectional area of the L1 coil to be 4 times that of the wire of the L2 coil, and so the wire should have twice the diameter, as the area is proportional to the square of the radius, and the square of 2 is 4. Don uses a white plastic tube as the former for his L1 primary coil winding. As you can see here, the wire is fed into the former, leaving sufficient clearance to allow the former to slide all the way into the outer coil. The wire is fed up inside the pipe and out through another hole to allow the coil turns to be made on the outside of the pipe. There appear to be 5 turns, but Don does not always go for a complete number of turns, so it might be 4.3 turns or some other value. The key point here is that the length of wire in the L1 coil turns should be exactly 1/4 of the length of wire in the L2 coil turns. The L2 coil used here is a commercial 3-inch diameter unit from Barker & Williamson, constructed from uninsulated, solid, single-strand tinned copper wire. How to make home-build versions is shown later on. Don has taken this coil and unwound 4 turns in the middle of the coil in order to make a center tap. He then measured the exact length of wire in the remaining section and made the length of the L1 coil turns to be exactly 1/4 of that length. The wire used for the L1 coil looks like Don's favorite jumbo speaker wire, which is a very flexible wire with a very large number of extremely fine uninsulated copper wires inside it. You will notice that Don has placed a plastic collar on each side of the winding, matching the thickness of the wire, in order to create a secure sliding operation inside the outer L2 coil, and the additional plastic collars positioned further along the pipe provide further support for the inner coil. This sliding action allows the primary coil L1 to be positioned at any point along the length of the L2 secondary coil, and that has a marked tuning effect on the operation of the system. The outer L2 coil does not have any kind of tube support, but instead, the coil shape is maintained by the stiffness of the solid wire plus 4 slotted strips. This style of construction produces the highest possible coil performance at radio frequencies. With a Tesla coil, it is most unusual to have the L1 coil of smaller diameter than the L2 coil. The L2 coil has 2 separate sections, each of 17 turns. One point to note is the turns are spaced apart using slotted strips to support the wires and maintain an accurate spacing between adjacent turns. It must be remembered that spacing coil turns apart like this alters the characteristics of the coil, increasing its capacitance factor substantially. Every coil has resistance, inductance and capacitance, but the form of the coil construction has a major effect on the ratio of these 3 characteristics. The coil assembly is held in position on the baseboard by 2 off-white plastic cable ties. The nearer half of the coil is effectively connected across the further half as shown in the circuit diagram above. One point which Don stresses, is that the length of the wire in the L1 coil and the length of wire in the L2 coil, must be an exact even division or multiple of each other. In this case, the L2 wire length in each half of the L2 coil is exactly 4 times as long as the L1 coil wire length. This is likely to cause the L1 coil to have part of a turn, due to the different coil diameters. For example, if the length of the L2 coil wire is 160 inches and L1 is to be 1/4 of that length, namely, 40 inches. Then, if the L1 coil has an effective diameter of 2.25 inches, allowing for the thickness of the wire when wound on a 2-inch diameter former, then the L1 coil would have 5.65, or 5 2/3, turns, which causes the finishing turn of L2 to be 240 degrees further around the coil former than the start of the first turn, that is, 5 full turns plus 2/3 of the 6th turn. The L1/L2 coil arrangement is a Tesla coil. The positioning of the L1 coil along the length of the L2 coil adjusts the voltage to current ratio produced by the coil. When the L1 coil is near the middle of the L2 coil, then the amplified voltage and amplified current are roughly the same. The exact wire ratio of these 2 coils gives them an almost automatic tuning with each other, and the exact resonance between them can be achieved by the positioning of the L1 coil along the length of the L2 coil. While this is a perfectly good way of adjusting the circuit, in the build shown in the photograph, Don has opted to get the exact tuning by connecting a capacitor across L1 as marked as C in the circuit diagram. Don found that the appropriate capacitor value was around the 0.1 microfarad, 100 nF, mark. It must be remembered that the voltage across L1 is very high, so if a capacitor is used in that position it will need a voltage rating of at least 9000 volts. Don remarks that the actual capacitors seen in the photograph of this prototype are rated at 15,000 volts, and were custom made for him using a self-healing style of construction. As has already been remarked, this capacitor is an optional component. Don also opted to connect a small capacitor across the L2 coil, also for fine-tuning of the circuit, and that component is optional and so is not shown on the circuit diagram. As the two halves of the L2 coil are effectively connected across each other, it is only necessary to have one fine-tuning capacitor. However, Don stresses that the height length of the coil, when standing vertically, controls the voltage produced while the coil width, the diameter of the turns, controls the current produced. The exact wire length ratio of the turns in the L1 and L2 coils gives them an almost automatic synchronous tuning with each other, and the exact resonance between them can be achieved by the positioning of the L1 coil along the length of the L2 coil. While this is a perfectly good way of adjusting the circuit, in the 1994 build shown in the photograph, Don has opted to get the exact tuning by connecting a capacitor across L1 as marked as C in the circuit diagram. Don found that the appropriate capacitor value for his particular coil build was about 0.1 microfarad, 100 NF, and so he connected two 47 NF high voltage capacitors in parallel to get the value which he wanted. It must be remembered that the voltage across L1 is very high, so a capacitor used in that position needs a voltage rating of at least 9000 volts. Don remarks that the actual capacitors seen in the photograph of this prototype are rated at 15,000 volts, and were custom made for him using a self-healing style of construction. Don has also connected a small capacitor across the L2 coil, and that optional component is marked as C2 in the circuit diagram, and the value used by Don happened to be a single 47 NF, high voltage capacitor. As the two halves of the L2 coil are effectively connected across each other, it is only necessary to have one capacitor for L2. There are various ways of dealing with the output from the L2 coil in order to get large amounts of conventional electrical power out of the device. The method shown here uses the four very large capacitors seen in the photograph. These have an 8000 or 9000 volt rating and a large capacity, and they are used to store the circuit power as DC prior to use in the load equipment. This is achieved by feeding the capacitor bank through a diode which is rated for both high voltage and high current, as Don states that the device produces 8000 volts at 20 amps, in which case, this rectifying diode has to be able to handle that level of power, both at startup when the capacitor bank is fully discharged and L2 is producing 8000 volts, and when the full load of 20 amps is being drawn. This capacitor bank is fed through a diode which is rated for both high voltage and high current, as Don states that the device produces 8000 volts at 20 amps, in which case, this rectifying diode has to be able to handle that level of power, both at startup when the capacitor bank is fully discharged and L2 is producing 8000 volts, and when the full load of 20 amps is being drawn. The actual diodes used by Don happen to be rated at 25 kV, but that is a far greater rating than is actually needed. In passing, it might be remarked that the average home user will not have an electrical requirement of anything remotely like as large as this, seeing that 10 kW is more than most people use on a continuous basis, while 8 kV at 20A is a power of 160 kW. As the neon tube driver circuit can put out 9000 volts, and since the L1/L2 coil system is a step-up transformer, if the voltage fed to the capacitor bank is to be kept down to 8000 volts, then the variac adjustment must be used to reduce the voltage fed to the neon tube driver circuit, in order to lower the voltage fed to the L1/L2 coil pair, typically, to 3000 volts. A very astute and knowledgeable member of the Yahoo EVGRAY forum, whose ID is Silver Healthio, has recently pointed out that Don Smith says quite freely that he does not disclose all of the details of his designs, and it is his opinion that a major item which has not been disclosed is that the diodes in the circuit diagrams shown here are the wrong way round, and that Don operates his voltages in reverse to the conventional way. In fact, the circuit diagram should be. He comments, the diodes leaving the neon tube driver may need to be reversed as we want to collect the negative polarity. The spark gap will then operate on ambient inversion and the spark will look and sound totally different with a much faster crack and producing very little heat, and even becoming covered in frost is possible. The variac should be raised up just enough to get a spark going, then backed off slightly. Any higher voltage is liable to make the neon tube driver think that it has a short circuit condition, and the new electronic designs will then shut down automatically and fail to operate at all if this method is not followed. When running, C, L1 and L2 operate somewhere up in the radio frequency band because the neon tube driver only acts as a tank circuit exciter. The large collection capacitor C3 should fill inverted to earth polarity as shown above. The load will then be pulling electrons from the earth as the cap is refilled back to zero rather than the joules in the capacitor being depleted. Also remember that the back EMF systems of John Bedini and others create a small positive pulse, but they collect a super large negative polarity spike which shoots off the bottom of an oscilloscope display. This is what we want, plenty of this stored in capacitors, and then let the ambient background energy supply the current when it makes the correction. This is a very important point, and it may well make a really major difference to the performance of a device of this nature. One reader has drawn attention to the fact that Don's main document indicates that there should be a resistor R across the L1 coil as well as the capacitor C, and he suggests that the circuit should actually be as shown above, considering what Don said earlier about his suitcase design. Another reader points out that the wire in the output choke shown in the photograph below appears to be wound with wire that is far too small diameter to carry the currents mentioned by Don. It seems likely that a choke is not needed in that position except to suppress possible radio frequency transmissions from the circuit, but a more powerful choke can easily be wound using larger diameter wire. When the circuit is running, the storage capacitor bank behaves like an 8000-volt battery which never runs down and which can supply 20 amps of current for as long as you want. The circuitry for producing a 220-volt 50 Hz AC output or a 110-volt 60 Hz AC output from the storage capacitors is just standard electronics. In passing, one option for charging the battery is to use the magnetic field caused by drawing mains frequency current pulses through the output choke coil, shown here. The output current flows through the left-hand winding on the brown cylindrical former, and when the photograph was taken, the right-hand winding was no longer in use. Previously, it had been used to provide charging power to the battery by rectifying the electrical power in the coil, caused by the fluctuating magnetic field caused by the pulsing current flowing through the left-hand winding, as shown here. The DC output produced by the 4 diodes was then used to charge the driving battery, and the power level produced is substantially greater than the minor current drain from the battery. Consequently, it is a sensible precaution to pass this current to the battery via a circuit which prevents the battery voltage rising higher than it should. A simple voltage level sensor can be used to switch off the charging when the battery has reached its optimum level. Other batteries can also be charged if that is wanted. Simple circuitry of the type shown in Chapter 12 can be used for controlling and limiting the charging process. The components on Don's board are laid out like this. Don draws attention to the fact that the cables used to connect the output of L2 to the output of the board, connecting the storage capacitors on the way, are very high voltage rated cables with special multiple coverings to ensure that the cables will remain sound over an indefinite period. It should be remarked at this point, that the outer 3 diameter coil used by Don is not wound on a former, but in order to get higher performance at high frequencies, the turns are supported with 4 separate strips physically attached to the turns, the technique described later in this document as being an excellent way for home construction of such coils. Please bear in mind that the voltages here and their associated power levels are literally lethal and perfectly capable of killing anyone who handles the device carelessly when it is powered up. When a replication of this device is ready for routine use, it must be encased so that none of the high voltage connections can be touched by anyone. This is not a suggestion, but it is a mandatory requirement, despite the fact that the components shown in the photographs are laid out in what would be a most dangerous fashion were the circuit to be powered up as it stands. Under no circumstances, Construct and test the circuit unless you are already experienced in the use of high voltage circuits or can be supervised by somebody who is experienced in this field. This is a one hand in the pocket at all times type of circuit, and it needs to be treated with great care and respect at all times, so be sensible. The remainder of the circuit is not mounted on the board, possibly because there are various ways in which the required end result can be achieved. The one suggested here is perhaps the most simple solution. The voltage has to be dropped, so an iron cord mains frequency step-down transformer is used to do this. To get the frequency to the standard mains frequency for the country in which the device is to be used, an oscillator is used to generate that particular mains frequency. The oscillator output is used to drive a suitable high-voltage semiconductor device, be it an FET transistor, an IGBT device, or whatever. This device has to switch the working current at 8000 volts, though admittedly, that will be a current which will be at least 36 times lower than the final output current, due to the higher voltage on the primary winding of the transformer. The available power will be limited by the current handling capabilities of this output transformer, which needs to be very large and expensive. As the circuit is capable of picking up additional magnetic pulses, such as those generated by other equipment, nearby lightning strikes, etc., an electronic component called a varistor marked V in the diagram, is connected across the load. This device acts as a voltage spike suppressor as it short-circuits any voltage above its design voltage, protecting the load from power surges. Don also explains an even more simple version of the circuit as shown here. This simplified circuit avoids the need for expensive capacitors and the constraints of their voltage ratings, and the need for electronic control of the output frequency. The wire length in the turns of coil L2 still needs to be exactly 4 times the wire length of the turns in coil L1, but there is only one component which needs to be introduced, and that is the resistor R placed across the primary winding of the step-down isolation transformer. This transformer is a laminated iron core type, suitable for the low mains frequency, but the output from L2 is at much higher frequency. It is possible to pull the frequency down to suit the step-down transformer by connecting the correct value of resistor R across the output transformer, or a coil and resistor, or a coil and a capacitor. The value of resistor needed can be predicted from the American Radio Relay League graph, shown as Fig 44 in Don's PDF document. The 6th edition of the Howard Sams Book Handbook of Electronics Tables and Formulas, ISBN 10-0672224690 or ISBN 13-978-0672224690, has a table which goes down to 1 kHz and so does not need to be extended to reach the frequencies used here. The correct resistor value could also be found by experimentation. You will notice that an earthed dual spark gap has been placed across L2 in order to make sure that the voltage levels always stay within the design range. Don also explains an even more simple version which does not need a variac, high voltage capacitors or high voltage diodes. Here, a DC output is accepted, which means that high frequency step-down transformer operation can be used. This calls for an air core transformer which you would wind yourself from heavy-duty wire. Mains loads would then be powered by using a standard off-the-shelf inverter. In this version, it is of course, necessary to make the L1 turns wire length exactly 1/4 of the L2 turns wire length in order to make the two coils resonate together. The operating frequency of each of these coils is imposed on them by the output frequency of the neon tube driver circuit. That frequency is maintained throughout the entire circuit until it is rectified by the 4 diodes feeding the low voltage storage capacitor. The target output voltage will be either just over 12 volts or just over 24 volts, depending on the voltage rating of the inverter which is to be driven by the system. The circuit diagram is. As many people will find the nomograph chart in Don's PDF document very difficult to understand and use, here is an easier version. The objective here is to determine the reactance or AC resistance in ohms, and the way to do that is as follows. Suppose that your neon tube driver is running at 30 kHz and you are using a capacitor of 100 NF, which is the same as 0.1 microfarad, and you want to know what is the AC resistance of your capacitor is at that frequency. Also, what coil inductance would have that same AC resistance. Then the procedure for finding that out is as follows. Draw a straight line from your 30 kHz frequency, purple line, through your 100 nanofarad capacitor value and carry the line on as far as the blue inductance line as shown above. You can now read the reactance, AC resistance, off the red line, which looks like 51 ohms to me. This means that when the circuit is running at a frequency of 30 kHz, then the current flow through your 100 NF capacitor will be the same as through a 51 ohm resistor. Reading off the blue inductance line, that same current flow at that frequency would occur with a coil which has an inductance of 0.28 millihenries. I have been passed a copy of Don's circuit diagram for this device, and it is shown here. The 4000V30MA transformer shown in this circuit diagram may use a ferrite cord transformer from a neon tube driver module which steps up the voltage, but it does not raise the frequency, as that is clearly marked at 120 Hz pulse DC. You will notice that the circuit diagram is drawn with plus shown below minus, which is most unusual. Please note that when an earth connection is mentioned in connection with Don Smith's devices, we are talking about an actual wire connection to a metal object physically buried in the ground, whether it is a long copper rod driven into the ground, or an old car radiator buried in a hole like Tyrrell Coppenads used, or a buried metal plate. When Thomas Henry Moray performed his requested demonstration deep in the countryside at a location chosen by the skeptics, the light bulbs which formed his demonstration electrical load glowed more brightly with each hammer stroke as a length of gas pipe was hammered into the ground to form his earth connection. Don also explains an even more simple version of his main device. This version does not need a variac, variable voltage transformer, or high voltage capacitors. Here, a DC output is accepted, which means that high frequency step-down transformer operation can be used. This calls on the output side, for an air core, or ferrite rod core, transformer which you would wind yourself from heavy-duty wire. Mains loads would then be powered by using a standard off-the-shelf inverter. In this version, it is of course, very helpful to make the L1 turns wire length exactly 1/4 of the L2 turns wire length in order to make the two coils automatically resonate together. The operating frequency of each of these coils is imposed on them by the output frequency of the neon tube driver circuit. That frequency is maintained throughout the entire circuit until it is rectified by the 4 diodes feeding the low voltage storage capacitor. The target output voltage will be either just over 12 volts or just over 24 volts, depending on the voltage rating of the inverter which is to be driven by the system. As the circuit is capable of picking up additional magnetic pulses, such as those generated by other equipment, nearby lightning strikes, etc., an electronic component called a varistor marked V in the diagram, is connected across the load. This device acts as a voltage spike suppressor as it short circuits any voltage above its design voltage, protecting the load from power surges. A gas discharge tube is an effective alternative to a varistor. This circuit is effectively 2 Tesla coils back to back, and the circuit diagram might be. It is by no means certain that in this circuit, the red and blue windings are wound in opposing directions. The spark gap, or gas discharge tube, in series with the primary of the first transformer alters the operation in a somewhat unpredictable way, as it causes the primary to oscillate at a frequency determined by its inductance and its self-capacitance, and that may result in megahertz frequencies. The secondary winding, S, of that transformer must resonate with the primary, and in the circuit which has no frequency compensating capacitors, that resonance is being produced by the exact wire length in the turns of the secondary. This looks like a simple circuit, but it is anything but that. The excess energy is produced by the raised frequency, the raised voltage, and the very sharp pulsing produced by the spark. That part is straightforward. The remainder of the circuit is likely to be very difficult to get resonating, as it needs to be in order to deliver that excess energy to the output inverter. When considering the length of wire in a resonant coil, it is necessary to pay attention to the standing wave created under those conditions. The wave is caused by reflection of the signal when it reaches the end of the wire or when there is a sudden change in the diameter of the wire, as that changes the signal reflection ability at that point in the connection. You should pay attention to Richard Quick's very clear description of this in the section of his patent which is included later on in this chapter. Also, remember what Don Smith said about locating the peaks of the standing wave by using a handheld neon lamp. One very significant thing which Don pointed out is that the mains electricity available through the wall socket in my home does not come along the wires from the generating station. Instead, the power station influences a local substation, and the electrons which flow through my equipment actually come from my local environment because of the influence of my local substation. Therefore, if I can create a similar influence in my home, then I no longer need that substation and can have as much electrical energy as I want, without having to pay somebody else to provide that influence for me. A practical implementation of one of Don Smith's designs. The objective here is to determine how to construct a self-powered, free energy electrical generator which has no moving parts, is not too expensive to build, uses readily available parts, and which has an output of some kilowatts. However, under no circumstances should this document be considered to be an encouragement for you, or anyone else, to actually build one of these devices. This document is presented solely for information and educational purposes, and as high voltages are involved, it should be considered to be a dangerous device unsuited to being built by inexperienced amateurs. The following section is just my opinions and so should not be taken as tried and tested, working technology, but instead, just the opinion of an inexperienced writer. However, questions from several different readers indicate that a short, reasonably specific description of the steps needed to attempt a replication of a Don Smith device would be helpful. Again, this document must not be considered to be a recommendation that you actually build one of these high-voltage, potentially dangerous devices. This is just information intended to help you understand what I believe is involved in this process. In broad outline, the following steps are used in the most simple version of the arrangement. 1. The very low frequency and voltage of the local mains supply is discarded in favor of an electrical supply which operates at more than 20,000 Hz, cycles per second, and has a voltage of anything from 350 volts to 10,000 volts. The higher voltages can give greater overall output power, but they involve greater effort in getting the voltage back down again to the level of the local mains voltage in order for standard mains equipment to be used. 2. This high-frequency high voltage is used to create a series of very rapid sparks using a spark gap which is connected to a ground connection. Properly done, the spark frequency is so high that there is no audible sound caused by the sparks. Each spark causes a flow of energy from the local environment into the circuit. This energy is not standard electricity which makes things hot when current flows through them, but instead this energy flow causes things to become cold when the power flows through them, and so it is often called cold electricity. It is tricky to use this energy unless all you want to do is light up a series of light bulbs, which incidentally, give out a different quality of light when powered with this energy. Surprisingly, the circuit now contains substantially more power than the amount of power needed to produce the sparks. This is because additional energy flows in from the ground as well as from the local environment. If you have conventional training and have been fed the myth of closed systems, then this will seem impossible to you. So, let me ask you the question: if, as can be shown, all of the electricity flowing into the primary winding of a transformer flows back out of that winding, then where does the massive, continuous flow of electricity coming from the secondary winding come from? None of it comes from the primary circuit, and yet millions of electrons flow out of the secondary in a continuous stream which can be supplied indefinitely. So, where do these electrons come from? The answer is from the surrounding local environment which is seething with excess energy, but your textbooks won't like that fact as they believe that the transformer circuit is a closed system, something which probably can't be found anywhere in this universe. 3. This high voltage, high frequency, high power energy needs to be converted to the same sort of hot electricity which comes out of a mains wall socket at the local voltage and frequency. This is where skill and understanding come into play. The first step is to lower the voltage and increase the available current with a step-down resonant transformer. This sounds highly technical and complicated, and looking at Don Smith's expensive Barker and Williamson coil, makes the whole operation appear to be one for rich experimenters only. This is not the case, and a working solution can be cheap and easy. It is generally not convenient to get the very high voltage all the way down to convenient levels in a single step, and so, one or more of those resonant transformers can be used to reach the target voltage level. Each step-down transformer boosts the available current higher and higher. 4. When a satisfactory voltage has been reached, we need to deal with the very high frequency. The easiest way to deal with it is to use high-speed diodes to convert it to pulsing DC and feed that into a capacitor to create what is essentially an everlasting battery. Feeding this energy into a capacitor converts it into conventional hot electricity, and a standard off-the-shelf inverter can be used to give the exact voltage and frequency of the local mains supply. In most of the world, that is 220 volts at 50 cycles per second. In America it is 110 volts at 60 cycles per second. Low-cost inverters generally run on either 12 volts or 24 volts, with the more common 12-volt units being cheaper. So, let's take a look at each of these steps in more detail and see if we can understand what is involved and what our options are. 1. We want to produce a high voltage, high frequency, low current power source. Don Smith shows a neon sign transformer module. His module produced a voltage which was higher than was convenient, and so he used a variable AC transformer, or variac as it is commonly known, to lower the input voltage and so lower the output voltage. There is actually no need for a variac, as we can handle the higher voltage, or alternatively, use a more suitable neon sign transformer module. However, we have a problem with using that technique. In the years since Don bought his module, they have been redesigned to include circuitry which disables the module if any current flows out of it directly to earth, and as that is exactly what we would want to use it for, so most, if not all, of the currently available neon sign transformer modules are not suitable for our needs. However, I'm told that if the module has an earth wire and that earth wire is left unconnected, that it disables the earth leakage circuitry, allowing the unit to be used in a Don Smith circuit. Personally, I would not recommend that if the module is enclosed in a metal housing. A much cheaper alternative is shown here. http://www.youtube.com/watch?v=rho_4d93q, where a small plasma globe circuit is used to generate a high frequency spark. It seems highly likely that one of those modules would suit our needs. An alternative method is to build your own power supply from scratch. Doing that is not particularly difficult, and if you do not understand any electronics, then perhaps reading the beginner's electronics tutorial in chapter 12, http://www.free-energy-info.com/chapter12.pdf, will fill you in on all of the basics needed for understanding, and probably designing your own, circuits of this type. Here is a variable frequency design for home construction. One advantage of this circuit is that the output transformer is driven at the frequency set by the 555 timer, and that frequency is not affected by the number of turns in the primary winding, nor its inductance, wire diameter, or anything else to do with the coil. While this circuit shows the rather expensive IRF9130 transistor, I expect that other P-channel FETs would work satisfactorily in this circuit. The IRF9130 transistor looks like this. The circuit has a power supply diode and capacitor, ready to receive energy from the output at some later date if that is possible and desired. The 555 circuit is standard, giving a 50% mark/space ratio. The 10NF capacitor is there to maintain the stability of the 555, and the timing section consists of two variable resistors, one fixed resistor and the 1NF capacitor. This resistor arrangement gives a variable resistance of anything from 100 ohms to 51.8K, and that allows a substantial frequency range. The 47K, linear, variable resistor controls the main tuning, and the 47K, linear, variable resistor gives a more easily adjustable frequency for exact tuning. The 100 ohm resistor is there in case both of the variable resistors are set to zero resistance. The output is fed through a 470 ohm resistor to the gate of a very powerful p-channel FET transistor, which drives the primary winding of the output transformer. The output transformer can be wound on an insulating spool covering a ferrite rod, giving both good coupling between the windings, and high frequency operation as well. The turns ratio is set to just 30:1 due to the high number of primary winding turns. With a 12-volt supply, this will give a 360-volt output waveform, and by reducing the primary turns progressively, allows the output voltage to be increased in controlled steps. With 10 turns in the primary, the output voltage should be 3600 volts, and with just 5 turns 7200 volts. The higher the voltage used, the greater the amount of work needed later on to get the voltage back down to the output level which we want. Looking at the wire specification table, indicates that quite a small wire diameter could be used for the oscillator output transformer's secondary winding. While this is perfectly true, it is not the whole story. Neon tube drivers are very small, and the wire in their output windings is very small diameter indeed. Those driver modules are very prone to failure. If the insulation on any one turn of the winding fails and one turn becomes a short circuit, then that stops the winding from oscillating, and a replacement is needed. As there are no particular size constraints for this project, it might be a good idea to use enameled copper wire of 0.45 mm or larger in an attempt to avoid this insulation failure hazard. No part of the transformer coil spool should be metal, and it would not be any harm to cover each layer of secondary winding with a layer of electrical tape to provide additional insulation between the coil turns in one layer and the turns in the layer on top of it. A plug-in board layout might be. Please remember that you can't just stick your average voltmeter across a 4 kV capacitor, unless you really do want to buy another meter, as they only measure up to about 1000 volts DC. So, if you are using high voltage, then you need to use a resistor divider pair and measure the voltage on the lower resistor. But what resistor values should you use? If you put a 10 megohm resistor across your 4 kV charged capacitor, the current flowing through the resistor would be 0.4 milliamps. Sounds tiny, doesn't it? But that 0.4 mA is 1.6 watts, which is a good deal more than the wattage which your resistor can handle. Even using this arrangement, the current will be 0.08 mA and the wattage per resistor will be 64 MW. The meter reading will be about 20% of the capacitor voltage, which will give a voltmeter reading of 800 volts. The input resistance of the meter needs to be checked and possibly allowed for, as the resistance in this circuit is so high, see Chapter 12. When making a measurement of this type, the capacitor is discharged, the resistor chain and meter attached, and then, and only then, is the circuit powered up, the reading taken, the input power disconnected, the capacitor discharged, and the resistors disconnected. High voltage circuits are highly dangerous, especially so, where a capacitor is involved. The recommendation to wear thick rubber gloves for this kind of work is not intended to be humorous. Circuits of this type are liable to generate unexpected high voltage spikes, and so, it might be a good idea to connect a varistor across the meter to protect it from those spikes. The varistor need to be set to the voltage which you intend to measure, and as varistors may not be available above a 300V threshold, 2 or more may need to be connected in series, where just one is shown in the diagram above. The varistor should not have a higher voltage rating than your meter. 2. We now need to use this high voltage to create a strategically positioned spark to a ground connection. When making an earth connection, It is sometimes suggested that connecting to water pipes or radiators is a good idea as they have long lengths of metal piping running under the ground and making excellent contact with it. However, it has become very common for metal piping to be replaced with cheaper plastic piping, and so any proposed pipe connection needs a check to ensure that there is metal piping which runs all the way into the ground. The spark gaps shown can be commercial high-voltage gas discharge tubes, adjustable homemade spark gaps with stainless steel tips about 1 mm apart, car spark plugs, or standard neon bulbs, although these run rather hot in this application. A 15 mm x 6 mm size neon bulb operates with only 90 or 100 volts across it. It would take a considerable number of them connected in series to create a high voltage spark gap, but it is probably a misconception that the spark gap itself needs a high voltage. Later on in this chapter, there is an example of a very successful system where just one neon bulb is used for the spark gap and an oscillating magnetic field. More than a meter wide is created when driven by just an old 2500 volt neon sign transformer module. If using a neon bulb for the spark gap, then an experienced developer recommends that a 22K resistor is used in series with the neon in order to extend its working life very considerably. This circuit is one way to connect the spark gap and ground connection. This is an adaptation of a circuit arrangement used by the forum member Slow and Easy on the Don Smith topic in the Energetic Forum. Here, he is using a low-glow neon transformer intended for use on a bicycle. The diodes are there to protect the high-voltage power supply from any unexpected voltage spikes created later on in the circuit. The spark gap is connected between the primary winding of a step-up transformer and the earth connection. No capacitor is used. Seeing this circuit, we immediately think of Don Smith's large and expensive coils, but this experimenter does not use anything like that. Instead, he winds his transformer on a simple plastic former like this. And to make matters worse, the primary winding wire is just 9 inches, 228.6 mm, long, and the secondary just 36 inches, 914.4 mm, long, the primary being wound directly on top of the secondary. Not exactly a large or expensive construction, and yet one which appears to perform adequately in actual tests. This is a very compact form of construction, but there is no necessity to use exactly the same former for coils, nor is there anything magic about the 9-inch length of the L1 coil, as it could easily be any convenient length, say 2 feet or 0.5 meters, or whatever. The important thing is to make the L2 wire length exactly 4 times that length, cutting the lengths accurately. It is common practice to match the weight of copper in each coil, and so the shorter wire is usually twice the diameter of the longer wire. The circuit above produces a cold electricity output of high voltage and high frequency. The voltage will not be the same as the neon transformer voltage, nor is the frequency the same either. The two coils resonate at their own natural frequency, unaltered by any capacitors. 3. The next step is to get the high voltage down to a more convenient level, perhaps, like this. Here, an identical transformer, wound in exactly the same way, is used in reverse, to start the voltage lowering sequence. The wire length ratio is maintained to keep the transformer windings resonant with each other. Supposing we were to wind the L2 coil of this second transformer in a single straight winding, and instead of winding just one L1 winding on top of it, 2 or more L1 identical windings were placed on top of it, what would happen? Now for a comment which will seem heretical to people steeped in the present day, inadequate, level of technology. The power flowing in these transformers is cold electricity, which operates in an entirely different way to hot electricity. The coupling between these coils would be inductive if they were carrying hot electricity, and in that case, any additional power take-off from additional L1 coils would have to be paid for by additional current draw through the L2 coil. However, with the cold electricity which these coils are actually carrying, the coupling between the coils is magnetic and not inductive, and that results in no increase in L2 current, no matter how many L1 coil take-offs there are. Any additional L1 coils will be powered for free. However, the position of the coils relative to each other has an effect on the tuning, so the L1 coil should be in the middle of the L2 coil, which means that any additional L1 coils are going to be slightly off the optimum tuning point. 4. Anyway, following through on just one L1 coil, there is likely to be at least one further step-down transformer needed, and eventually, we need conversion to hot electricity. Probably the easiest conversion is by feeding the energy into a capacitor and making it standard DC. The frequency is still very high, so high-speed diodes, such as the 75 nanosecond UF54008, are needed here, although the voltage level is now low enough to be no problem. The DC output can be used to power an inverter so that standard mains equipment can be used. It is not necessary to use just one, expensive, large capacity inverter to power all possible loads, as it is cheaper to have several smaller inverters, each powering its own set of equipment. Most equipment will run satisfactorily on square wave inverters, and that includes a mains unit for powering the input oscillator circuit. PVC pipe is not a great material when using high-frequency high-voltage signals, and gray PVC pipe is a particularly poor coil former material. The much more expensive acrylic pipe is excellent, but if using PVC, then performance will be better if the PVC pipe is coated with an insulating lacquer, or table tennis balls dissolved in acetone as shown on YouTube. However, there are some other factors which have not been mentioned. For example, if the L1 coil is wound directly on top of the L2 coil, it will have roughly the same diameter, and so, the wire being 4 times longer, will have roughly 4 times as many turns, giving a step-up or step-down ratio of around 4:1. If, on the other hand, the coil diameters were different, the ratio would be different, as the wire lengths are fixed relative to each other. If the L2 coil were half the diameter of the L1 coil, then the turns ratio would be about 8:1, and at 1/3 diameter, 12:1, and at a quarter diameter, 16:1, which means that a much greater effect could be had from the same wire length by reducing the L2 coil diameter. However, the magnetic effect produced by a coil is linked to the cross-sectional area of the coil, and so a small diameter is not necessarily at great advantage. Also, the length of the L1 coil wire and number of turns in it affect the DC resistance, and more importantly, the AC impedance, which affects the amount of power needed to pulse the coil. It is also thought that having the same weight of copper in each winding gives an improved performance, but what is not often mentioned is the opinion that the greater the weight of copper, the greater the effect. You will recall that Joseph Newman, Chapter 11, uses large amounts of copper wire to produce remarkable effects. So, while 9 inches and 36 inches of wire will work for L1 and L2, there may well be improved performance from longer lengths of wire and or thicker wires. We should also not forget that Don Smith pointed out that voltage and current act out of phase and in opposite directions along the L2 coil, moving away from the L1 coil. It has been suggested that a greater and more effective power output can be obtained by splitting the L2 coil underneath the L1 coil position, winding the second part of L2 in the opposite direction, and grounding the junction of the two L2 windings. Don doesn't consider it necessary to reverse the direction of winding. The result is an L2 winding which is twice as long as before and arranged like this. Here, the additional high voltage diodes allow the two out-of-phase windings to be connected across each other. You will notice that this arrangement calls for two separate earth connections, both of which need to be high-quality connections, something like a pipe or rod driven deeply into moist soil, or alternatively, a metal plate or similar metal object of substantial surface area, buried deep in moist earth, and a thick copper wire or copper braid used to make the connection. These earthing points need to be fairly far apart, say, 10 meters. A single earth connection can't be used, as that would effectively short-circuit across the L1/L2 transformer, which you really do not want to do. With this arrangement, the outline circuit becomes. The thick earth wiring is helpful because in order to avoid the earth wire being included in the resonant wire length, you need a sudden change in wire cross-section. These are just some ideas which might be considered by some experienced developer who may be thinking of investigating Don Smith-style circuitry. To give you some idea of the capacity of some commercially available wires when carrying hot electricity, this table may help. It is recommended that the wire have a current carrying capacity of 20% more than the expected actual load, so that it does not get very hot when in use. The wire diameters do not include the insulation, although for solid enameled copper wire, that can be ignored. There is a most impressive video and circuit shown at http://utuesday.be/q3vr6qmolw where a very simple arrangement produces an immediately successful performance for the front end of Don's circuitry. The circuit appears to be here, a simple neon sign transformer module which has no earth connection, is used to produce a 2.5 kV voltage with a frequency of 25 kHz and a maximum output current capacity of 12 mA. There is no difficulty in constructing the equivalent to that power supply unit. The two outputs from the module are converted to DC by a chain of 41N4007 diodes in series in each of the two outputs, each chain being inside a plastic tube for insulation. This output is fed through an optional 22K resistor via a neon lamp to a microwave oven capacitor which happens to be 874 NF with a voltage rating of 2100 volts. You might feel that the voltage rating of the capacitor is too low for the output voltage of the neon sign module, but the neon has a striking voltage of just 90 volts and so the capacitor is not going to reach the output voltage of the power supply. The resistors are solely to extend the life of the neons as the gas inside the tube gets a considerable jolt in the first nanosecond after switch on. It is unlikely that omitting those resistors would have any significant effect, but then, including them is a trivial matter. The second neon feeds the primary of the resonant transformer which is only shown in notional outline in the diagram above as the developer suggests that the primary acts as a transmitter and that any number of receiving coils can be used as individual secondaries by being tuned to the exact frequency of that resonating primary. In the video showing this arrangement, the developer demonstrates the fluctuating, high-frequency field which extends for some 4 feet, 1.2 m, around the coil. He also remarks that the single neons in his arrangement could each be replaced with 2 neons in series. In test which I ran, I found that I needed 2 neons in series ahead of the capacitor in order to get continuous lighting of the output neon. Also, one of the diodes needed to be reversed so that one faced towards the input and one away from it. It did not matter which diode was reversed as both configurations worked. Again, please note that this presentation is for information purposes only and it is not a recommendation that you should actually build one of these devices. Let me stress again that this is a high voltage device made even more dangerous by the inclusion of a capacitor, and it is quite capable of killing you, so, don't build one. The developer suggests that it is an implementation of the transmitter section of Don's transmitter/multiple receivers design shown below. However, before looking at that design, there is one question which causes a good deal of discussion on the forums, namely, if the center tap of the L2 secondary coil is connected to ground, then should that earth connection wire length be considered to be part of the quarter length of the L1 coil? To examine this possibility in depth, the following quote from Richard Quick's very clear explanation of resonance in his U.S. patent 7,973,296 of July 5, 2011 is very helpful. However, the simple answer is that for there to be exact resonance between 2 lengths of wire, whether or not part, or all of those lengths of wire happen to be wound into a coil, then one length needs to be exactly 4 times as long as the other, and ideally, half the diameter as well. At both ends of both lengths of wire, there needs to be a sudden change in wire diameter and Richard explains why this is. But, leaving that detailed explanation for now, we can use that knowledge to explain the above simplified system in more detail. Here is the circuit again. One very important point to note is that no earth connection is required and in spite of that, the performance shown on video is very impressive. While an earth connection can feed substantial power into the circuit, not needing one for the front end is an enormous advantage and potentially, opens the way for a truly portable device. Another very important point is the utter simplicity of the arrangement, where only cheap, readily available components are used, and not many of those are needed. The resistors for extending the life of the neon bulbs are not shown, but they can be included if desired, and the circuit operation is not altered significantly by having them there. If a higher spark voltage is wanted, then 2 or more neon bulbs can be used in series, where these circuit diagrams show just one. A point to note is that the lower diode is shown reversed when compared to the previous diagram. This is because the power supply shown is any generic power supply which drives a simple output coil which does not have a center tap. The neon supply of the earlier diagram appears to have 2 separate outputs which will, presumably, be out of phase with each other, as that is common practice for neon sign driver modules. If you wish, the 2 diodes shown here could be replaced by a diode bridge of 4 high voltage, high speed diodes. The wire lengths of L1 and L2 are measured very accurately from where the wire diameter changes suddenly, as indicated by the red dashed lines. The L2 wire length is exactly 4 times as long as the L1 wire length, and the L2 wire diameter is half of the L1 wire diameter. How long is the L1 wire? Well, how long would you like it to be? It can be whatever length you want, and the radius of the L1 coil can be whatever you want it to be. The theory experts will say that the L1 coil should resonate at the frequency of the power feeding it. Well, good for them, I say, so please tell me what frequency that is. It is not going to be the frequency of the power supply, as that will be changed by at least one of the neon bulbs. So, what frequency will the neon bulb produce? Not even the manufacturer could tell you that, as there is quite a variation between individual bulbs which are supposedly identical. Actually, it doesn't matter at all, because the L1 coil, and the L2 coil, if you measure them accurately, has a resonant frequency all of its own, and it will vibrate at that frequency no matter what the frequency feeding it happens to be. A coil resonates in very much the same way that a bell rings when it is struck. It doesn't matter how hard you strike the bell or how rapidly you strike it, the bell will ring at its own natural frequency. So the L1 coil will resonate at its own natural frequency no matter what rate the voltage spikes striking it arrive, and as the L2 coil has been carefully constructed to have exactly that same frequency, it will resonate in synchronization with the L1 coil. This means that the length of the wire for the L1 coil is the choice of the builder, but once that length is chosen, it determines the length of the wire for the L2 coil, as that is exactly 4 times as long, unless the builder decides to use an arrangement which has L2 wound in both the clockwise and counterclockwise directions, in which case, each half of the L2 coil will be 4 times the length of the wire in the L1 coil, like this. Mind you, there is one other factor to be considered when deciding what the most convenient wire length for L1 might be, and that is the number of turns in the L1 coil. The larger the ratio between the turns in L1 and the turns in L2, the higher the voltage boost produced by the L1/L2 transformer, and remember that the length of L2 is fixed relative to the length of L1. So, a possible circuit style might be. There are some important points to remember. One is that there must be a sudden change of wire diameter at both ends of each L1 coil and at the ends of each L2 coil. If there isn't, then the connecting wire length will form part of the coil, and if there is some change in diameter but not very much, then it is anybody's guess what the resonant wire length for that coil will be. There can be as many step-down isolation air core L1/L2 transformers as desired, and these do not need to be particularly large or expensive. The builder of the circuit put it together in just a few minutes, using components which were to hand, including the microwave oven capacitor Mark C in the diagrams above. That capacitor is isolated on both sides by the neon bulb spark gaps, and so it will have no modifying effect on the resonant frequency of any of the coils in this circuit. But it is vital to understand that the energy stored in that capacitor can, and will, kill you instantly if you were to touch it, so let me stress once again that this information is not a recommendation that you actually build this circuit. The DC output from the circuit is intended to power a standard inverter, which in turn, would be perfectly capable of powering the high voltage, high frequency input oscillator. One final point is that, as demonstrated in the video, the oscillating magnetic field produced by the L1 coil can power several identical L2 coils, giving several additional power outputs for no increase in input power, because the coupling is magnetic and not inductive as mentioned earlier in this chapter. Please notice that neither the L1 coil nor the L2 coil has a capacitor connected across it, so resonance is due solely to wire length and no expensive high-voltage capacitors are needed to get every L1/L2 coil pair resonating together. One possible arrangement might be like this, where two of the L2 coils are shown connected together to give increased output power. This arrangement uses low-voltage inexpensive components for the output stages, and there is no obvious limit to the amount of output power which could be provided. As the circuit operates at high frequency throughout, there is no particular need for additional L2 coils to be placed physically inside the L1 coil. However, there can be an advantage to this arrangement in that the wire length of the L1 coil is greater, which in turn makes the wire length of each L2 coil greater, being 4 times longer. This gives greater flexibility when planning the turns ratio of the L1/L2 transformer. The voltage step up or step down of that transformer happens to be in the ratio of the turns, in spite of the fact that this is not inductive coupling and so standard transformer technology does not apply. When you choose the number of turns and coil diameter for L1, that also gives the length of the L2 wire. In order to get the desired output voltage, if perhaps, the step-down ratio is needed to be an amount of 46:1, then you need 46 times the number of L1 turns on the L2 coil. That means that you know both the wire length and number of turns wanted in the L2 coil. But, as each turn will have a length of 3.14159 times the diameter, it follows then that the wanted diameter is the wire length per turn, divided by 3.14159. The wire sits on top of the tube on which it is wound and so has a greater diameter by 1 wire thickness, so the calculated tube diameter needs to be reduced by 1 wire diameter. For example, if the length per turn is 162 mm and the wire diameter 0.8 mm, then the tube diameter would be 162/3.14159 which is 50.766 mm, just over 2 inches. Now for Richard's explanation of the resonant frequency of any length of wire. Quarter wave resonance, standing electromagnetic waves. One of the two main types is electrical resonance, is referred to here as quarter wave resonance. This type of resonance depends almost entirely on the length of a wire element for reasons described below. If a segment or length of wire is 1/4 as long as the voltage waves which are traveling through the wire, then a set of reflected waves will be added to the emitted waves, in a synchronized alignment which creates stronger superimposed waves. Accordingly, an understanding of the quarter wave phenomenon will help a reader understand how a straightforward and easily controlled factor, i.e., the length of a wire ribbon which will be used to form a spiral coil, can help create a quarter wave resonant response, which will create the types of electromagnetic pulses and fields referred to as standing waves. The speed at which a voltage impulse is transmitted through a metal wire is extremely fast. It is essentially the same as the speed of light, which travels 300 million meters, 186,000 miles, in a single second. That distance would circle the Earth more than 7 times. If wavelength, in meters, is multiplied by frequency, cycles per second, the result will be the speed of light, 300 million meters/second. Therefore, the wavelength of an alternating current, AC, voltage, at some particular frequency, will be the speed of light, divided by which frequency. Therefore, using simple division, if an alternating voltage operates at a frequency of 1 MHz, which is a million cycles per second, then the wavelength at that frequency will be 300 meters. If the frequency has become 500 kHz, the wavelength becomes twice as long, 600 meters, and, if the frequency were to increase to 2 MHz, the wavelength drops to 150 meters. It should be noted which the term cycles is what scientists call a dimensionless unit, which drops out and becomes silent when other physical terms are multiplied or divided. At AC frequencies of 10 kHz or greater, the common references to alternating current, AC, voltage begin using a different term, which is radio frequency, RF, voltage. Accordingly, RF voltage is a form, or subset, of AC voltage, which operates at frequencies higher than 10 kHz. RF power generators are readily available, and are sold by numerous companies which can be easily located by an internet search, using the term RF power generator. For example, Hotech Technologies Incorporated. HotechTech.com sells two RF power generators, called the AG1024 and AG1012 models, which can provide output power at frequencies ranging from 20 kHz to 1 MHz. The 1012 model has a power output of 1000 watts, while the 1024 model has a power output of 2000 watts. The output frequency of any such RF power supply can be adjusted and tuned across the entire range of operating frequencies, merely by turning knobs or manipulating other controls in a power supply of this type. In a wire having a fixed and unchanging length, the easiest way to create a standing wave is to adjust the RF frequency emitted by a power supply with an adjustable frequency, until the tuned frequency creates a wavelength which is 4 times as long as the wire. This principle is well known to physicists, and it is commonly referred to as quarter wave behavior, since the length of the wire segment must be 1/4 as long as the wavelength. Since it is important to this invention, the principles behind it are illustrated in a series of drawings provided in Fig 1 to Fig 4, all of which are well-known prior art. Fig 1a indicates an idealized wavelength of an alternating voltage, depicted by a sine wave which is being sent from an AC power supply, shown by a circle at the left end of a horizontal straight wire, into the input end of the wire. The voltage waves travel through the wire towards the right, as indicated by the block arrow in Fig 1a. When the waves reach the end of the wire, they cannot leave the wire, at least, not in a simplified and ideal system, which is being assumed and used here to explain the principle of how a simple straight wire can create a standing wave. Therefore, the voltage wave will effectively bounce or reflect back from the tip of the wire. And the reflected wave will begin traveling back through the wire, going in the opposite direction, as indicated by the left-pointing block arrow in Fig 1b. Because of the laws of conservation of energy, the reflection and return travel of these types of waves, when they bounce off the tip of a wire, is actually quite good, and rather efficient, as discussed below, provided which the wire tip does not emit sparks, arc discharges, or other forms of escaping electrical energy. Accordingly, Fig 1a depicts a set of emitted waves traveling towards the right, while Fig 1b depicts an idealized set of reflected waves traveling toward the left along the same wire. Fig 1c illustrates what happens when both sets of waves, emitted and reflected, are superimposed on each other. Since the two sets of waves are traveling at exactly the same speed, and since they have exactly the same wavelength, they will create a standing wave pattern when they are added together. As can be visualized from Fig 1c, there will be a set of locations, along the length of the wire, which can be referred to as peak nodes, where the AC voltage reaches its maximum. At a location halfway between a pair of adjacent peak nodes, there will be a spot which can be called a null node, a zero node, a through or valley node, or similar terms. At each null node location, the AC voltage will appear to be not fluctuating at all. Those are the sites, along the length of the wire, where each positive hump, created by a sine wave traveling toward the right, will be counterbalanced and offset by a negative hump with exactly the same height, traveling at an identical speed toward the left. As a result, this type of response within a wire creates a standing wave. If the instantaneous voltage is measured at a null node, it would appear that nothing is happening, in terms of fluctuating voltage. Furthermore, the null node will not be moving, along the length of the wire, instead, it will appear to be standing still. This can be demonstrated, in a coil, by using a grounded lead to test for voltages along the length of a coil. If a grounded lead coupled to a voltmeter is used to touch the surfaces of a series of strands in a non-insulated coil, such as a coil made of thin copper tubing, wrapped around a plastic cylindrical shape, as used in the types of large transformers used by hobbyists to create Tesla coils which will emit large and visually impressive electrical arcs, the test lead will detect no apparent voltage at a null node, which will occur at some particular strand in the coil. At a different strand of the coil, the test lead will detect an alternating voltage which has twice the strength and intensity of the voltage being emitted by the power supply. If voltage is measured at a peak node, the voltage will be doing something which can be called, using vernacular or layman's terms, the full tilt boogie. The AC voltage levels will be moving back and forth, between, I, a very high and intense positive voltage, to, an equally intense negative voltage. This is indicated by the bubble shapes shown along the wire in Fig 1c. The bubbles which are shown in Fig 1c can help someone understand how standing waves are created, and how they act in a synchronized manner. However, which drawing fails to show another result which is very important in what actually happens in a standing wave. For purposes of description and analysis at this introductory level, the system can be assumed to be ideal, which implies a perfect mirror image reflection of each wave from the right end of the wire. An ideal system also implies that no reflections occur at the left-hand end of the wire where the power supply is located, and all reflected wave activity simply ceases. In real circuits and wires of this type, second and third order reflections do in fact occur, and they are used to further increase the strength and power output of these types of systems. However, those additional factors and harmonics should be ignored until after the basic principles of this type of system have been grasped and understood. In an ideal system, when the reflected waves, which are traveling toward the left, in the wire segments illustrated in Fig 1, are superimposed on the emitted waves, traveling toward the right, the peak positive voltage which will be instantaneously reached, at the highest point of each bubble shown in Fig 1c, will occur when the positive peak of an emitted wave crosses a mirror image positive peak of a reflected wave, traveling in the opposite direction. Accordingly, when those two positive peak values are added to each other, the instantaneous positive peak voltage which will occur, in the wire, will actually be twice as intense as the positive peak voltage being emitted by the AC power supply. An instant later, at that exact point on that segment of wire, a negative peak voltage will be created, which will be the sum of, I, the negative peak voltage emitted by the power supply, and, 2, the negative peak voltage of a reflected wave also will pass through, traveling toward the left. At which instant, when those two negative peak voltages are added to each other, the instantaneous negative voltage which will occur, in the wire, will be twice as intense as the negative peak voltage being generated by the AC power supply. A more accurate and representative visual depiction of a standing wave in a wire would actually show the heights of the peaks as being twice as tall as the peaks of the emitted voltage waves, and the reflected voltage waves. However, which depiction might confuse people, so it usually is not shown in drawings of standing waves. Accordingly, the instantaneous response in the wire, at a location halfway between two null nodes, is doing something which can fairly and properly be called the full tilt double-double boogie. The double-double phrase, note which it contains not just one but two doubles, was added to that phrase, for two reasons. I, to emphasize the fact that each and every voltage peak, maximum positive, and maximum negative, will be twice as strong, and twice as intense, as the maximum positive and negative peak voltages emitted by the power supply, and, 2, to point out that the frequency of the superimposed bubbles, shown in Fig 1c, is actually twice as fast as the frequency of the AC cycle which is emitted by the power supply, as discussed below. The twice the intensity result is directly comparable to what an observer will see, if a large mirror is placed behind a light bulb in an otherwise dark room. The mirror effectively keeps the room dark, everywhere behind the mirror, so there is no magical doubling of the light in the room, which would violate the basic law of conservation of energy. Instead, what the mirror does is to shift light away from the backside of the mirror, and keep that light energy on the reflective side of the mirror. Anyone standing in front of the mirror will see two apparent light bulbs. Both of those light bulbs, the original bulb, and the reflected image, will have the same brightness, if the mirror is perfect. Therefore, the mirror will double the intensity of the light energy reaching the observer. That same effect, in a circuit, will happen if the end of a wire acts like a mirror. If a wire does not have any components which will cause it to become an active emission source, which is the behavior of transmission antennas and certain other components, in a way which efficiently releases voltage-created energy into the atmosphere, then the basic rules which require conservation of energy will prevent that energy from simply disappearing and ceasing to exist. As a result, even if the end of a wire is not designed to be a perfect reflector, a large portion of the voltage wave will indeed reflect off the wire tip, and travel back through the same wire, in a second pass. To understand adequately the type and amount of wave reflection which occurs at a wire tip, consider what happens if a light bulb is shining in a room which has shiny, glossy white paint on all the walls and ceilings. Then, consider how it would look if the same light bulb were located in a room with all of the walls and ceilings painted matte black. The total amount of light which would be available, to carry out a task such as reading a newspaper, clearly would be much greater in the white room, because light reflects off white paint, even though white paint does not even begin to approach the type of reflection quality or clarity which a mirror creates. The difference in what happens, when light intensity in a room painted matte black is compared to a room painted a glossy white, does not arise from the presence or absence of reflection quality or clarity. Instead, it is governed by the laws of conservation of energy. When light shines onto a surface which is painted matte black, the light energy is absorbed by the paint, and it literally warms the paint up. In contrast to that, glossy white paint will not absorb light energy, so it reflects the light back out, for a second pass through the air which fills a room. Because of the laws of conservation of energy, and without depending on any quality of reflectance characteristic of wire tips, electrical energy cannot simply disappear, when it reaches the end of a wire. Instead, there are only two things which can happen to that energy. The electrical energy can be emitted into the surroundings, such as by emitting sparks, arcs, or radio frequency signals which will carry energy, or, 2, if the energy is not emitted by the tip of the wire, then, by simple necessity and because of the basic law of conservation of energy, it must be reflected back into the wire, and it will be forced to travel back through the wire again. If a wire has a long and tapered tip, then the reflected wave might become somewhat diffused, and it might lose some portion of the clarity of the wave. However, since wavelengths in the frequencies of interest here are hundreds of meters long, the type of tip created by a conventional wire cutter will not create any significant diffusion in a reflected wave. And, unlike the white painted walls of a room, there is not a large area which is available, at the tip of a wire, which can create scatter, spread, or diffusion. As a result, the tip of a wire will be a relatively efficient mirror-type reflector, when an AC voltage is pumped into one end of the wire. The second factor mentioned above, when the double-double boogie phrase was mentioned, relates to a doubling of the frequency of a standing wave. When a standing wave is created in a wire by reflection of an emitted AC voltage wave, the frequency of the standing wave is, quite literally, double the frequency of the emitted wave. This can be seen, visually, by noting that in the emitted AC voltage, shown in Fig 1a, a single complete wavelength contains both a positive hump and a negative hump. Accordingly, 3 complete sine waves, divided into 3 segments by the imaginary vertical lines, are shown in Fig 1a. By contrast, each and every bubble shown in Fig 1c depicts a complete and total wavelength, in a standing wave. 6 of those standing wave bubbles fit into exactly the same length of wire which holds only 3 emitted wavelengths from the power supply. The frequency doubling effect of standing waves is important, because AC systems can convey and release energy in a manner which increases, as the frequency of the AC voltage supply increases. To some extent, this is analogous to saying that, If a motor can be run at twice the speed, while still generating the same torque, then the work output of that motor can be twice as great, at the higher speed. That analogy is not entirely accurate, since work output from an electric device which uses AC power depends on area of the curve functions which occur when sine waves are involved. Nevertheless, as a general principle, if the frequency of the voltage peaks increases, then power output will also increase, in many types of electric circuit components. In the three panels of Fig 1, the wire length is 3 times as long as the wavelength of the voltage from the power supply. However, to create standing waves, a wire length does not need to be any particular multiple of the wavelength of an AC voltage. As can be seen by considering Fig 1c, the same types of bubbles would be created, if the wire length were exactly twice as long as the wavelength, or, 2, if the wire length were the same length as the wavelength. Accordingly, Fig 2, which includes Fig 2a showing an emitted wave, Fig 2b showing a reflected wave, and Fig 2c showing the superimposed bubbles, shows what happens in a wire segment which has a length which is equal to a single wavelength from an AC voltage at a fixed frequency. A resonant standing wave will be formed, with a frequency which is double the frequency of the input AC voltage. Which same result will apply, in a wire having any length which is an exact, integer, multiple, such as 1x, 2x, 3x, etc., of the wavelength of the AC voltage being pushed, or forced, driven, pumped, etc., into the wire segment. Moving to still shorter wires, the same principle also applies to any wire with a length equal to 1/2 of an AC voltage wavelength. As shown in Fig 3, which includes Fig 3a showing an emitted wave, Fig 3b showing a reflected wave, and Fig 3c showing the superimposed bubbles, if the wire length is 1/2 of the wavelength, a natural and resonant standing wave will still form, with a frequency which is double the frequency of the input AC voltage. Finally, moving to a still shorter wire, the same principle also applies to any wire which has a length equal to 1/4 of an AC voltage wavelength, as shown in Fig 4a, Fig 4b, and Fig 4c even though it does not stretch across or cover a complete bubble. The standing wave shown in Fig 4c is nevertheless a stable, natural, and resonant standing wave, with a frequency which is exactly twice the frequency of the input AC voltage. It is possible to create partially stable and semi-resonant responses, using 1/8, 1/16, or shorter lengths of wire, by using additional devices which can remove electrical power from the system, or which can generate effects which are usually called harmonics. However, those are not the types of natural and stable responses which can be created by a simple, basic system consisting of nothing more than a wire having a fixed length and a reflective tip, and 2. An AC power source with a frequency which can be tuned until it creates a resonant response in any wire segment having a suitable length. Therefore, since quarter wave wire lengths are the shortest lengths which can create natural and stable standing waves, the conventional term which is commonly used to describe what happens when a wire creates a resonant standing wave response is a quarter wave response. In some devices, telescoping components, or other elements which can alter the effective length of a wire-type element, can be used to alter the ability of the element to respond to a fixed wavelength. Many types of antennas use this approach, if they need to process signals which are being transmitted on fixed and known frequencies. However, those examples are not relevant to spiral coil reactors, which will use an approach which involves tuning and adjusting the frequency of the voltage which is being supplied to a reactor, until a resonant response is observed in coils with fixed and unchanging lengths. It should also be noted that certain types of tuning elements, such as capacitors, which can have either fixed or adjustable capacitance levels, can also be coupled electrically to a wire, in a manner which emulates adding more length to that wire. This approach can be used to alter, or increase the range of, the frequencies to which a wire circuit will respond resonantly. So, If we have resonant standing wave voltages in our L2 coil and some of that signal passes through the wire connecting one end of the coil to the earth, then what will happen? The best way to check it is to test the way which a prototype behaves. However, if I may express an opinion, I would suggest that the signal passing down the earth wire will be absorbed when it reaches the earth, and that will prevent the signal being reflected back to the L2 coil to upset its operation. The third of Don's designs which we can consider is particularly attractive because almost no home construction is needed, all of the components being available commercially, and the output power being adaptable to any level which you want. Don particularly likes the circuit because it demonstrates COP1 so neatly, and he remarks that the central transmitter Tesla coil on its own is sufficient to power a household. The coil in the center of the board is a power transmitter made from a Tesla coil constructed from two Barker and Williamson ready-made coils. 3 more of the inner coil are also used as power receivers. The outer, larger diameter coil is a few turns taken from one of their standard coils and organized so that the coil wire length is 1/4 of the coil wire length of the inner coil, L2. As before, a commercial neon tube driver module is used to power the L1 outer coil with high voltage and high frequency. It should be understood that as power is drawn from the local environment each time the power driving the transmitter coil L1 cycles, that the power available is very much higher at higher frequencies. The power at mains frequency of less than 100 Hz is far, far less than the power available at 35,000 Hz, so if faced with the choice of buying a 25 kHz neon tube driver module or a 35 kHz module, then the 35 kHz module is likely to give a much better output power at every voltage level. The L1 short outer coil is held in a raised position by the section of white plastic pipe in order to position it correctly relative to the smaller diameter L2 secondary coil. The secondary coils are constructed using Barker and Williamson's normal method of using slotted strips to hold the tinned, solid copper wire turns in place. As there are very slight differences in the manufactured coils, each one is tuned to the exact transmitter frequency, and a miniature neon is used to show when the tuning has been set correctly. The key feature of this device is the fact that any number of receiver coils can be placed near the transmitter and each will receive a full electrical pickup from the local environment, without altering the power needed to drive the Tesla coil transmitter, more and more output without increasing the input power, unlimited COP values, all of which are over 1. The extra power is flowing in from the local environment where there is almost unlimited amounts of excess energy, and that inflow is caused by the rapidly vibrating magnetic field generated by the central Tesla coil. While the additional coils appear to just be scattered around the baseboard, this is not the case. The YouTube video http://www.youtube.com/watch?v=tine Hertz room 4Z4 feature related demonstrates that the pickup of these coils is affected to a major degree by the distance from the radiating magnetic field. This is to do with the wavelength of the signal driving the Tesla coil, so the coils shown above are all positioned at exactly the same distance from the Tesla coil. You still can have as many pickup coils as you want, but they will be mounted in rings around the Tesla coil, and the coils in each ring will be at the same distance from the Tesla coil in the center. Each of the pickup coils act exactly the same as the L2 secondary coil of the Tesla coil transmitter, each picking up the same level of power. Just as with the actual L2 coil, each will need an output circuit arrangement as described for the previous device. Presumably, the coil outputs could be connected in parallel to increase the output amperage, as they are all resonating at the same frequency and in phase with each other. Each will have its own separate output circuit with a step-down isolation transformer and frequency adjustment as before. If any output is to be a rectified DC output, then no frequency adjustment is needed, just rectifier diodes and a smoothing capacitor following the step-down transformer, which will need to be an air core or ferrite core type due to the high frequency. High voltage capacitors are very expensive. The http://www.richieburnett.co.uk/parts.html website shows various ways of making your own high voltage capacitors and the advantages and disadvantages of each type. There are 2 practical points which need to be mentioned. Firstly, as the Don Smith devices shown above feed radio frequency waveforms to coils which transmit those signals, it may be necessary to enclose the device in an earthed metal container in order not to transmit illegal radio signals. Secondly, as it can be difficult to obtain high voltage high current diodes, they can be constructed from several lower power diodes. To increase the voltage rating, diodes can be wired in a chain. Suitable diodes are available as repair items for microwave ovens. These typically have about 4000 volt ratings and can carry a good level of current. As there will be minor manufacturing differences in the diodes, it is good practice to connect a high-value resistor, in the 1 to 10 megohm range, across each diode, as that ensures that there is a roughly equal voltage drop across each of the diodes. If the diode rating of these diodes were 4 amps at 4000 volts, then the chain of 5 could handle 4 amps at 20,000 volts. The current capacity can be increased by connecting 2 or more chains in parallel. Most constructors omit the resistors and find that they seem to get satisfactory performance. The impedance of a coil depends on its size, shape, method of winding, number of turns and core material. It also depends on the frequency of the AC voltage being applied to it. If the core is made up of iron or steel, usually thin layers of iron which are insulated from each other, then it can only handle low frequencies. You can forget about trying to pass 10,000 cycles per second, Hertz, through the coil, as the core just can't change its magnetic poles fast enough to cope with that frequency. A core of that type is okay for the very low 50 Hz or 60 Hz frequencies used for mains power, which are kept that low so that electric motors can use it. For higher frequencies, ferrite can be used for a core, and that is why some portable radios use ferritorod aerials, which are a bar of ferrite with a coil wound on it. For higher frequencies, or higher efficiencies, iron dust encapsulated in epoxy resin is used. An alternative is to not use any core material, and that is usually referred to as an air core coil. These are not limited in frequency by the core, but they have a very much lower inductance for any given number of turns. The efficiency of the coil is called its Q, for quality, and the higher the Q factor, the better. The resistance of the wire lowers the Q factor. A coil has inductance, and resistance caused by the wire, and capacitance caused by the turns being near each other. However, having said that, the inductance is normally so much bigger than the other two components that we tend to ignore the other two. Something which may not be immediately obvious is that the impedance to AC current flow through the coil depends on how fast the voltage is changing. If the AC voltage applied to a coil completes one cycle every 10 seconds, then the impedance will be much lower than if the voltage cycles a million times per second. If you had to guess, you would think that the impedance would increase steadily as the AC frequency increased. In other words, a straight line graph type of change. That is not the case. Due to a feature called resonance, there is one particular frequency at which the impedance of the coil increases massively. This is used in the tuning method for AM radio receivers. In the very early days, when electronic components were hard to come by, variable coils were sometimes used for tuning. We still have variable coils today, generally for handling large currents rather than radio signals, and we call them rheostats, and some look like this. These have a coil of wire wound around a hollow former, and a slider can be pushed along a bar, connecting the slider to different winds in the coil depending on its position along the supporting bar. The terminal connections are then made to the slider and to one end of the coil. The position of the slider effectively changes the number of turns of wire in the part of the coil which is being used in the circuit. Changing the number of turns in the coil changes the resonant frequency of that coil. AC current finds it very, very hard to get through a coil which has the same resonant frequency as the AC current frequency. Because of this, it can be used as a radio signal tuner. If the coil's resonant frequency is changed to match that of a local radio station by sliding the contact along the coil, then that particular AC signal frequency from the radio transmitter finds it almost impossible to get through the coil, and so it, and only it, diverts through the diode and headphones as it flows from the aerial wire to the earth wire, and the radio station is heard in the headphones. If there are other radio signals coming down the aerial wire, then, because they are not at the resonant frequency of the coil, they flow freely through the coil and don't go through the headphones. This system was soon changed when variable capacitors became available, as they are cheaper to make and they are more compact. So, instead of using a variable coil for tuning the radio signal, a variable capacitor connected across the tuning coil did the same job. While the circuit diagram above is marked tuning capacitor, that is actually quite misleading. Yes, you tune the radio receiver by adjusting the setting of the variable capacitor, but what the capacitor is doing is altering the resonant frequency of the coil/capacitor combination, and it is the resonant frequency of that combination which is doing exactly the same job as the variable coil did on its own. This draws attention to two very important facts concerning coil/capacitor combinations. When a capacitor is placed across a coil in parallel as shown in this radio receiver circuit, then the combination has a very high impedance, resistance to AC current flow, at the resonant frequency. But if the capacitor is placed in series with the coil, then there is nearly zero impedance at the resonant frequency of the combination. This may seem like something which practical people would not bother with. After all, who really cares? However, it is a very practical point indeed. Remember that Don Smith often uses an early version, off-the-shelf neon tube driver module as an easy way to provide a high voltage, high-frequency AC current source, typically 6,000 volts at 30,000 Hz. He then feeds that power into a Tesla coil, which is itself a power amplifier. The arrangement is like this. People who try to replicate Don's designs tend to say, I get great sparks at the spark gap until I connect the L1 coil and then the sparks stop. This circuit can never work because the resistance of the coil is too low. If the resonant frequency of the L1 coil does not match the frequency being produced by the neon tube driver circuit, then the low impedance of the L1 coil at that frequency will definitely pull the voltage of the neon tube driver down to a very low value. But if the L1 coil has the same resonant frequency as the driver circuit, then the L1 coil, or the L1 coil/capacitor combination shown on the right, will have a very high resistance to current flow through it, and it will work well with the driver circuit. So, no sparks, means that the coil tuning is off. It is the same as tuning a radio receiver. Get the tuning wrong and you don't hear the radio station. This is very nicely demonstrated using simple torch bulbs and two coils in the YouTube video showing good output for almost no input power. http://www.youtube.com/watch?v=KQDCWDC bony. And while only one resonant pickup coil is shown, there is the possibility of using many resonant pickup coils with just the one transmitter. With a coil, fancy name inductor and symbol L, AC operation is very different to DC operation. The coil has a DC resistance which can be measured with the ohms range of a multimeter, but that resistance does not apply when AC is being used, as the AC current flow is not determined by the DC resistance of the coil. Because of this, a second term has to be used for the current controlling factor of the coil, and the term chosen is impedance, which is the feature of the coil which impedes AC current flow through the coil. The impedance of a coil depends on its size, shape, method of winding, number of turns and core material. It also depends on the frequency of the AC voltage being applied to it. If the core is made up of iron or steel, usually thin layers of iron which are insulated from each other, then it can only handle low frequencies. You can forget about trying to pass 10,000 cycles per second, Hertz, through the coil, as the core just can't change its magnetic poles fast enough to cope with that frequency. A core of that type is okay for the very low 50 Hz or 60 Hz frequencies used for mains power, which are kept that low so that electric motors can use it. For higher frequencies, ferrite can be used for a core, and that is why some portable radios use ferritorod aerials, which are a bar of ferrite with a coil wound on it. For higher frequencies, or higher efficiencies, iron dust encapsulated in epoxy resin is used. An alternative is to not use any core material, and that is usually referred to as an air core coil. These are not limited in frequency by the core, but they have a very much lower inductance for any given number of turns. The efficiency of the coil is called its Q, for quality, and the higher the Q factor, the better. The resistance of the wire lowers the Q factor.